Hello, dear students. Today we are going to learn the first lesson for the first quarter in Math 7, which involves sets. By the way, this is teacher Mary Jane, and I will be guiding you as we learn about sets. Here are the subtopics that we are going to learn for today. Introduction to sets, Venn diagrams, and set operations. The focus of our lessons will be on the following most essential learning competencies or MELCs. First is illustrates well-defined sets, subsets, universal sets, null set, cardinality of sets, union and intersection of sets, and the difference of two sets. Another one, or number 2, is for you learners to be able to solve problems involving sets with the use of Venn diagrams. By definition, a set is a collection of well-defined objects or things. When we say well-defined, it means that these objects have common characteristics. Okay, so we call these objects or things as an element or an object. But the most common term that we use is element. That's why it says there, each object of a set is called an element or object of the set. Now the symbol that we will use is this. So that is the symbol, or that is the Greek letter. That is the Greek letter epsilon. Okay, we call it epsilon. Now, a set is usually denoted or named using capital letters. So take note of that. We use capital letters to denote sets, and its elements are denoted by small letters that are enclosed by braces. So you should be familiar what braces looks like. So these are braces. That is different from this. So this is a parenthesis. So that is wrong. You cannot use that to denote sets, okay, or to enclose elements of a set. Now here are some examples of sets. So we have for number 1, set A. So we call this set A. This is its name, and these are its elements. We call the numbers inside as elements, and those elements are separated by commas. That's why for number 1 there are 5 elements, namely 1, 2, 3, 4, and 5, which are enclosed by braces. So these are the braces. Another example for number 2, the name of the set is set B, and its elements are A, E, I, O, U. And I know that you know those are the vowels in the English alphabet. Another example, you can also write sets that includes names. Okay, for number 3, we have set C, and its elements are names. So we have Anna, Rhea, Rachel, and Maria. Okay, for number 4, we have the colors of the rainbow. So we have red, orange, yellow, green, blue, and indigo. For number 5, we have set E, and we have there the name of some national heroes. So we have Rizal, Bonifacio, and Del Pilar, as well as Nabini. So here are some examples of sets. Now let us try this activity as we list the elements of the following. So now for number 1, we are going to list down the set of odd counting numbers. Are you familiar with odd numbers? Okay, odd numbers are numbers which cannot be divided exactly, or which cannot be divided exactly by 2. So it has a remainder of 1. So what are those odd numbers? Of course, the lowest is what? So the lowest odd number is 1, followed by 3, followed by 5, followed by 7, and so on. Since there are a lot of numbers that follows after 7, so we use this symbol that is called ellipsis. Okay, ellipsis. It composes of 3 consecutive dots. Okay, and we follow the rules or the definition of set a while ago. As we said a while ago that we use capital letters to name them. Since we are talking about odd numbers, I'm going to use capital O to name this set. And then after that, equal sign, we put an equal sign and then enclose our elements using braces. So once again, since number 1 or the set of odd counting numbers are infinite, or there are unlimited number of odd counting numbers, so we are going to use ellipsis. Okay, so that is for number 1. Number 2, how about the set of even counting numbers? Again, we start by naming our set. So we can use letter E for even, or you can use any letter that you want. Now, the lowest even number is 2. By the way, even numbers are numbers which can be divided exactly by 2. So we have 2, 4, 6, 8, 10. And again, since there are more numbers that follows after 10, so we use an ellipsis, or we use ellipsis. Okay, so that is for number 2. Now, how about 0? What do you think? Is it odd or even? So 0, is it odd or even before we proceed? So 0 can be divided by 2. That's why we consider this as an even number. Okay, but we did not include it in number 2 since it says there counting number, and the lowest counting number is 1. That's why for number 2 we start with 2. But in case it says a set of even numbers, so we may start with 0. I hope that you were able to take note of that. Number 3, set of prime numbers. I'll give you a clue. So prime numbers are numbers which have exactly 2 factors. Okay, exactly 2 factors. And what are those 2 factors? It's the number itself and 1. So when we say factors, it is the number which can divide the number exactly, which can exactly divide a certain number. Okay, so if we are going to answer that, we start by naming our set. So we have set P, and then we use braces, and the lowest prime number or uh, prime counting number is 2. Okay, followed by 3, since 2 and 3 2 can only be divided by 2 and 1. 3 can be divided by 3 and 1 only, followed by 5. 5 has only 2 factors, followed by 7, and followed by 11, and I will use ellipses. Okay, so that is the set of prime numbers starting from 2. So take note, 2 is the only even number that is prime. Okay, only even number that is prime. Apart from 2, there are no other prime numbers that are even. Okay, number 4, set of composite numbers. So if a prime number has exactly 2 factors, a composite number has 3 or more factors. It means that this number can be divided by 3 or can be exactly divided by 3 or more numbers. The lowest composite number or counting number that we can write is 4. Why? Because 4 has 3 factors, namely 1, 2, and 4. Right? Because 4 divided by 1 is 4, 4 divided by 2 is 2, and 4 divided by 4 is 1. So those are the factors of 4, followed by 6. Then we have 8, we have 9. What's next? We have, we have, let's erase that. Before 12, we can write we can have 10 followed by 12 and so on. So those are the composite numbers. And how about 1? So 1, remember, I'll put it here. 1 is neither. When we say neither, it is not prime, it is not composite, because it has only one factor, in which that factor is 1 itself. Okay, 1 can only be divided by 1. And let's continue with number 5, the set of the multiples of 5. When we say multiple, this is the result when we multiply that certain number by our counting numbers. Okay, starting with 1. So when we multiply 5 times 1, the result is 5. 5 times 2, 10. 5 times 3, 15, and so on. We write then M as the name of our set, but again, you can use other letters if you want. Let's start with 5, followed by 10, 15, 20, 25, and so on. So those are the multiples of 5. For number 6, set of the factors of 20. So the factors of 20, when we say factors, again, these are the numbers which could exactly divide 20. And to list it down, we write first the name of the set. So I'll use the letter F. The lowest factor of 20 is 1. It can also be divided by 2, followed by 4, followed by 5, and then 10, and then 20. This time I will not use ellipses because these are the only factors of 20. We have 1, 2, 4, 5, 10, and 20. For number 7, it says there the set of consonants in the English alphabet. What are our consonants? So we have, let me name that first. So we have C, and then we have B as the first consonant, followed by C, D, F, G, This time I will use ellipsis, but I will end it with Z, meaning we have letter B, C, D, F, G. There are more numbers between G and Z. I mean, there are more letters between G and Z. Okay, so that has a limit, which is Z. So unlike the examples for 1 to 5, which have infinite number of elements, for number 7, it has a finite number of elements. So later on, we will have more examples of finite versus infinite sets. Just take note of this notation. So again, comma, and then I'll put uh, 3 dots or ellipses, and then comma, and then we have the last element, which is Z. And then for number 8, we have the set of vowels. I'll use letter V. In the English alphabet, we start, of course, with A, followed by E, I, O, and U. Those are the elements or the set of vowels in the English alphabet. Number 9, the set of colors in the rainbow. I will use R this time for rainbow. 8, rainbow. And we have a limited space. I will just use the acronym or first letter of each color. So we have R for red, O for orange, Y for yellow, G for green, B for blue, I for indigo, and V for violet. Take note of that acronym if you are still not familiar with the colors of the rainbow. And for number 10, we will skip this because you have different sectionings in your school. Okay, let's continue. The next lesson is the different ways of writing sets. You have already encountered one way. Okay, so here are the two ways of writing sets. Again, you have encountered one, okay, or this method, which is the roster method. The roster method is a method used by listing down all the elements of a set. We simply list down the elements. Just like these examples, we have the name of the set, and then we have the braces, and inside those braces are the elements separated by a comma or commas. Another example number 2. So the elements are already listed down. And we have here some notes. We name sets using capital letters, and we've done that in the previous examples. For number 2, the elements of a set are enclosed by braces. Again, we use braces, and we do not use parentheses or what do we call this? Bracket. Okay, we use this for braces. A parenthesis. Okay, that is a parenthesis, and that is a bracket. So again, we do not use these two symbols. This is the correct one. Yeah. Using that method of using the rule method, let us list down the elements using the roster method. Okay, let us answer this first before we continue. For number one, again, that is read as set A is the set of all x such that x is an odd number from 1 to 10. What are the odd numbers from 1 to 10? First, I will rewrite the name of the set. So we have set A, and then odd numbers from 1 to 10. We have 1, followed by 3, followed by 5, 7, and then 9. This one is in rule, and these are in roster, or these are written using roster method. Okay, number two, we have set P is the set of all x such that x is a prime number between 11 and 20. I have given you the definition of prime number a while ago. Okay, so what is the prime number between 11 and 20? We start with 13. Why? Why did we not include 11? Because we have here the term between. It means that we don't have, or we should not include 11 because we are only considering the numbers between 11 and 20. The first element is 13, followed by 17, and then we have 19. So those are the only elements of set P. Next, number 3, we have set O is a set of all x such that x is an odd counting number. Okay, again, odd counting number, so we have set O. I will name that as set O, and then we have again 1. I'll fix my braces. 1 followed by 3 followed by 5, 7, 9. There is no limit to it. That's why I'm going to use ellipses. Number 4, set E is the set of all x such that x is an even counting number greater than 10. So that is the condition. Again, we copy the name of the set, and then what is the next counting number or even counting number after 10? We have 12, followed by 14, 16, 18. We cannot list out all of it. I'm just going to use ellipsis or put an ellipsis. Number 5, set C is the set of all x such that x is a composite number less than 4 but greater than 0. Again, composite number less than 4 but greater than 0. It says they're less than, so the numbers less than 4 are 3, 2, and 1. Okay, but none of those is a composite number. That's why for set C, we will put an empty braces. Okay, an empty brace without elements. So there is no element. Another way of writing an empty set is using this symbol. Okay, this is another way of writing a null or empty set. And for number 6, we have set F, the set of all x such that x is a factor of 9. We name that as F, and the factors of 9 are 1, 3, and 9. That's it. So that is the answer for number 6. Now for you to have a guide, if you are still unfamiliar with odd and even numbers, I have here a table. The numbers in purple are odd numbers, while the numbers with no colors or plain white are even numbers. And then for letter B, I have here a table of the prime and composite numbers from 1 to 100. So if you have noticed, 1 here is neither green nor white. It is shaded blue because we have said a while ago that it is neither prime nor composite. So it is not considered prime and it is not considered composite. Now the numbers in white are prime numbers. So it has only 2 factors. And if you are going to count all of them, there are 25 prime numbers from 1 to 100. And then we have the composite numbers. These are the numbers in green. Okay, so how many composite numbers do we have from 1 to 100? If we are going to subtract 25 minus 1, so 26, 100 minus 26, we have 74 composite numbers from 1 to 100. The next part of the lesson is on cardinality of a set. This is very easy. Cardinality of a set is determined by the number of elements contained in a set. We simply count the number of elements in a set. For example, we have here set A with elements 2, 4, 6, 8, and 10. We are just going to count how many elements does it have, and that is the answer, or that is the cardinality. To denote cardinality, we put small letter n and then the set enclosed by a parenthesis. After that, we count the number of elements. So we have 1, 2, 3, 4, and 5. The cardinality of set A is 5. Okay, when you see the symbol that is read as the cardinality of set A is 5. For letter B or example B, so we have set B with elements A, B, C. Again, to denote its cardinality, so we use small letter n and then parenthesis enclosing letter B or the name of the set. We have here cardinality of set B is 3 since set B has 3 elements. Okay, that is for cardinality of a set. The next one or the next part is the difference between finite and infinite set. You have encountered this, or I have discussed some of this in the previous example. Anyway, here are the definition of the two. Finite set has a definite number of elements. Definite, when you say definite, it has a limited number of elements, or it is countable. Okay, we can count it. While an infinite set has an unending number of elements when listed. Okay, unending, it means that even if you write all of its elements, it has no end. Okay, that is an infinite set. Now I have here a short activity. I'm going to show you a set and you're going to identify if it is finite or infinite. Number 1, is it finite or infinite? Obviously it is finite. Number 2, that is infinite, of course, because it used an ellipsis and there is no number after the ellipsis. Number 3, so that is again an infinite set. Number 4, set of odd counting numbers less than 100. It has a limit. Okay, by the way, this is written using our rule method, and it says there odd counting number less than 100. It has a limit. That's why this is a finite set. Number 5, again in rule method, and it says their prime number between 5 and 10. It has a limit, so that is a finite set. Number 6, composite number greater than 16. So the word greater than makes it an infinite set because there are a lot of numbers greater than 16. And let's continue with the difference between a subset and a superset. If A and B are sets and every element of A is also an element of B, then we can say that A is a subset of B denoted by this symbol, or equivalently, B is a superset of A denoted by this. So remember, when we say subset, the subset is always the one which faces or which this part of our symbol faces. Okay, and then the opening part, whatever it faces, that is the superset. Okay, so in this case, since the opening is in this area, so we can see that B is the superset, and A is the subset. Okay, again, this is the superset and the subset is this one. So if A is a subset of B but A is not equal to B, for example, there exists at least one element of B which is not an element of A, then we call it a proper or strict subset, or a proper or strict superset. Okay, we remove the equal sign and simply write this symbol. So that is for proper subset, and this is the symbol for proper superset. Here is an example. There are 5 sets. Set A with elements from 1 to 10. Set B with elements 2, 4, 6, and 8. Set C with elements 3, 6, 9, and 12. Set D with elements 2, 4, and 8. And set E with elements 3, 6, 9, and 12. So we are just going to answer whether the following is true or false. Okay. For number 1, we have that is read as A is a superset of B, meaning are all of the elements of set B in set A. Let us check. So 2, we have 2, 4 is also in A, 6 is in A, and 8 is also in A, which means that number 1 is true. Number 2, that is read as B is a subset of C, meaning all of the elements of set B in set C. Let us check. So 2 is 2 in set C? No, it's not. So based on that first element, we can say that number 2 is false. Number 3, D is a superset of A. That means all of the elements of set A are in set D. Let us check. So 1 is 1 in set D, so it is not. That's why based on that, again, we have a false statement. Number 4, that is read as A is a subset of E. Are all the elements of set A in set E? Of course not. Okay, from the first element 1, we cannot find it in set E, so number 4 is false. Number 5, B is a superset of D. Does set B contain all of the elements of set B? Let us check. So 2 is in B, 4 is in B, and 8 is in B. So number 5 is true. Number 6, C is a subset of E. Let us check. C is a, no, I should say C is a superset of E. Well, all of the elements, let us check if all of the elements of set E are in set C. And yes, we have 3, 3, 6, 6, 9, 9, 12, and 12. They have the same elements, so it is proper that we put this symbol under this curve. Okay, so that is true. Number 7, D is a subset of A. So let's check if all of the elements of D are in A. So 2, 4, and 8. All of the elements are there. So this is also true. Here are more examples. This time it focuses only on subsets. Okay, subsets. We have here condition. List down the subsets of set A. So when we say a subset, it contains the elements of a certain set or of a given set. So let's check. The answer here is 1 followed by 2. Take note, if you are going to write subsets, it should be enclosed by by braces, okay, to denote that it is a set. So we have first written each of the elements of the set. Okay, so we started with 1, only 1, followed by 2, and then 3, and then after that we've combined two numbers. So we have 1 and 2, followed by 1 and 3, 2 and 3. After that, if we don't have any other combinations, we write the all of the elements, which are 1, 2, and 3, and of course we have the empty or null set. Okay, so that, remember that the empty or null set is always a subset of any set. Okay, when you're listing down, you may start with a null set right away or empty set. Okay. Now there is a question here, how many elements are in set A? So we have 1, 2, and 3. There are 3 elements. Now how many subsets did it have? Let us count. So we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, we are asking this, or it is being asked, because there is actually a formula that we can use to determine how many subsets does a certain set have based on the number of its elements. Here is another example. So we are going to list down the subsets of set B. How many elements are in set B? Okay, we will answer that once we can answer that right now. So the number of elements are 4, and then here are the subsets. Again, we start by listing down the individual elements. So we have 2, 4, and then 6, and then 8, and then we combine by 2's. We have 2 and 4, 2 and 6, 2 and 8, followed by 4 and 6, 4 and 8, 6 and 8, and then after the combination of two numbers, we continue with 3 numbers, so 2, 4, and 6, followed by 2, 4, and 8, then 2, 6, 8, 4, 6, 8, and then 2, 4, 6, 8, followed by the null or empty set. If we are going to count, That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Later on, I will show you the formula. Okay, so here it is. What did you notice? So if you are given these numbers of elements, so if you are given an empty set, okay, empty set because it has no element at all, so it has only one subset. And what is that subset? That is the null or the empty set. And of course, it has no proper subset at all, because if you're going to remove that, we don't have any proper subset at all, okay, because it has only one. Another, if we have a set having only one element, then the number of subsets it have is only two, okay, and that includes the null set and the set itself. Okay, if removing one, that the number of proper subsets it have is 1. Next, if we have a set with two elements, the number of subsets it have is 4. Removing one, we have 3 proper subsets, and so on. So these are the examples a while ago. 3 elements and then 4 elements. So if we have 5, we have 32 proper subsets, 32 subsets and 31 proper subsets. 6, there are 64 subsets and 63 proper subsets. Now, if you don't, whatever the number of element is, we use this formula. To get the number of subsets, we simply write 2, and then the exponent will be the number of elements. So for instance, we have we have a set having 10 elements. How do you determine the number of subsets? So we have 2 raised to 10. If we expand that, we have 2 times 2 times 2, that will be 10 times 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. If you're going to solve that, so we have 2 times 2, 4, 4 times 2 is 8, 8 times 2, 16, 16 times 2 is 32, 32 times 2 is 64, 64 times 2, 128, 128 times 2 is 256, 256 times 2 is 512, and 512 times 2 is 1024. Okay, that means that a set having 10 elements have a total number of subsets, which is 1024. When we remove the proper subset, when we remove the other set containing all of the elements or all of the 10 elements, so the number of proper subsets is 1023. Imagine if I'm going to let you list down all of those, right? Okay, anyway, let's continue. Let's try this. List down the subsets of set C with elements A, E, I, O, U. So those are our vowels. First, let us answer this question. How many elements are in set C? So we have 5. And then how many subsets does it have? Let us use the formula a while ago. So we have 2 raised to 5. 2 times 2 times 2 times 2 times 2. So we have 32. We should be able to list down the 32 subsets of this. So I'll start with writing the null set or empty set, followed by A, the set containing only A, and then we have E, and then we have I, we have O, followed by U. Okay, we have listed down the individual elements. This time, let's combine two elements in one set. We start with A and E. Then we have A and I. We also have AO, AU. Since we're done with A and U, we start with letter E as the first element. So E and I. We also have E and O. What else? E and U. Okay, we're done with E as the first element. So let's have I as the first element, and then O, I, and U. Next, we have O as the first element, and of course U as the second element. I think we are done with two elements. Let's take three elements. Let's start with A, E, I. What else? A, E, O. And then A, E, U. And then let's have A, I, O. A, I, U. And then A, O, U. We're done with A as the first element. Let's continue with E as the first element. So we have E, I, O, E, I, U. Are we done? We can still have E as the first letter, and then O is the second letter, and then U. So E, O, U. This time we have I as the first letter, I, O, U. We're done with combination of three. We continue with combination of four. We have A, E, I, O, A, E, I, U. What else? A, I, O, U. And then E, I, O, U. Then all of the elements A, E, I, O, U. Let's check if we have 32. Let's use another ink. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. Let us check where we missed. Again, that is the pi at the null set, and then A, E, I, O, U, A, E, A, I, A, O, A, U. Okay, let's check first. Okay, so what we're missing here is the combination of the four letters A, E, O, U. Okay, so when we count all of that, there are 32 subsets. Okay, when we remove this, we will have 31 proper subsets. Okay, so that is the answer to this activity. Now we have already encountered the null or empty set. Let us just define it. a set which has no element, the cardinality of a null set is 0, and the symbol we use is either this or this, an empty braces. A null set has one subset, which is the null set itself. We also have what we call the equal and equivalent sets. Let's see the difference between the two. Equal sets are sets which have the same cardinality and have the same elements. On the other hand, we have equivalent sets. These are sets that have the same number of elements only. Okay, so what we are considering for equivalent sets is the number of elements. So if they are the same, then we consider that as equivalent sets. And if they have the same cardinality, at the same time they have exactly the same elements, then they are called equal sets. These are the symbols that we will use for equal sets in the equal sign. And for equivalent sets, we have this symbol. Okay, so we have these examples. Given set A, B, C, D, and E with the given elements, we can infer that C is equal to D. Why? C and D have 1 and 2 as its elements, even though the order is different, but we can still see that they have the same elements, and of course they have 2 elements each. So now C is equal to D. Another one, B is also equal to E because they have exactly the same elements. At the same time, they have 3 elements each. Now we can say that A is equivalent to B because A and B both have 3 elements. So disregarding the elements, since they both have the same elements, so we can say they are equivalent. A is also equivalent to set E because they have 3 elements each. B is also equivalent to E because they have 3 elements. They both have 3 elements, and C is equivalent to D because they both have 2 elements. So those are the symbols that we will use for equal and equivalent sets. So what is the lowest even prime number based on our examples a while ago? That's right. The answer is 2. Next. What is the cardinality of a set containing the factors of 5? Okay, again, when we say cardinality, it refers to the number of elements. Okay, of a set containing the factors of 5. What are the factors of 5? 5 can only be divided by 1 and 5. So when asked about the cardinality, we write it this way: small letter n and then f. So there are only 2 elements, so the cardinality of the set containing the factors of 5 is 2. That is the answer. 2 is the answer to this question. Question number 3. Question number 4. What is the cardinality of set A? Set A is the set of all x such that x is a letter in the English alphabet. Okay, so we know that there are 26 letters in the English alphabet. So the cardinality of set A is 26. Question number 5. Given set A with elements 1, 2, 3, 4, 5 until 10, which of the following is a proper subset of A? which is of the following is a proper subset of A? Let us check. For set B, we have 1, 3, 5, 7. All of those are in set A, so set B is a proper subset. Set C, we have 1, 2, 3, 4, 5 in set A, so this is a proper subset. Next, 5, 10, 15, and 20. 5 and 10 are the only element of set A. We don't have 15 and 20. That's why set D is not a proper subset. Next, set E, there is no 11, 12, 13, 14, and 15 in set A, so this is not a proper subset. For set F, we have 1, 2, 3, 4 until 10 as its element. Remember the definition of proper subset. It should have at least one element that is not an element of the other set. Okay, since they are equal sets, so this is not a proper subset of set A. Okay, so that is for question number 5. Let's continue with lesson 2. This involves the set operations. We are going to learn 4. We have the union, intersection, complement, and difference between two sets. First, let us answer these questions. So we have true or false. Determine whether the following statement is true or false. We are given set K with elements 3, 4, 7, 8, 9, and 10. Set L with elements 4, 7, and 9. And set M with elements 4, 7, and 10. Okay, number 1. 7 is an element of K. Of course, yes. So this is true. Number 2, 8 is an element of L. We cannot see an 8 here, so this is false. Number 3, 10 is a subset of M. What did I say? When writing a set, it should be enclosed by braces. Since this is not enclosed by braces, it is just a number, so this is false. Number 4, 4, okay, a set containing 4 as an element is a subset of K. Yes, that is true. Number 5, 9 is an element of L. Since this is enclosed by braces, it means that it is a set. So a set cannot be an element of a certain set. Okay, so this is false. Number 6, null set is a subset of M. Of course, we have said a while ago that the null set is always a subset of any set, so this is true. Number 7, set L is equal to set M. When we say equal, they should have exactly the same elements, but since they only have 4 and 7 as common elements, so this is false. Number 8, 0 is an element of a null set. That is false because we have said that a null set has no element at all. Number 9, L is an element of K. The elements of set K are 3, 4, 7, 8, 9, and 10. This is false. Number 10, M is a subset of K. All of the elements of set M are in K, so this is true. Number 11, L is a subset of M. Of course, this is false because they have different elements or different third elements. Number 12, K is a finite set. That is true. Number 13, L is a proper subset of K. since all of the elements 4, 7, and 9 are in K, this is true. 14, M is a superset of K. That is false. It should be the reverse. K is the superset of M. Number 15, the cardinality of set L is 3. Yes, that is true because it has 3 elements. And number 16, this is for our next lesson, but that is read as the cardinality of the union of set K and set L is 9. Well, that is false. The answer should be 6. Okay, we will learn about this later on. Let's start with the union of sets. The union of sets A and B, written as A union B, is the set of elements that belong to either A or B or both. Here are some examples. We have set A with elements A, N, E, and T. Set B with elements P, O, and Y. So how are we going to get the union of these two? So we simply combine all of the elements of these two sets. Okay, so we have A and ET. These are the elements of set A, and then we have the elements of set B, which are P, O, and Y. However, there is something wrong with this answer. Okay, so N was repeated. Okay, they have a common element N. That's why we have to remove the other one. That's why the answer to this, or the union of set A and B, is A, N, E, T, P, O, and Y. Take note of that. So when listing down the elements or the union of two sets, we make sure that there are no repeated elements. Okay, so this is the correct one, and this one is wrong. And this is how it looks. This is how the union of two sets look like. Okay, we have this set, set A, and then set B. This is their intersection. Here are more examples. So we have set A with elements 1, 3, 5, 7, and 9. Set B with elements 2, 4, 6, and 8. And set C with elements 1, 2, 3, 4, 5, and 6. To get the union of set A and set B, we simply list down its elements. Okay, so we have written it in ascending order. So we have the union of set A and set B is 1, 2, 3, 4, 5, 6, 7, 8, and 9. So the numbers in the numbers in red are the elements of set A, and the numbers in blue are the elements of set B. Next, number 2, the union of set B and set C is 1, 2, 3, 4, 5, 6, and 8. Again, that is 1, 2, 3, 4, 5, 6, and 8. For the union of set C and set A, we simply combine. I'm going to write it here. So we have 1 is the lowest number, followed by 2, followed by 3, 4, 5, 6, and then 7, and then 9. Okay, so that is the answer to number 3. Next, we have here the definition for intersection of sets. the intersection of sets A and B, written as this. So this is the symbol for intersection, and read as A intersection B is formed by getting the elements that are common to both A and B. So they should both have that element. Here is an example. Given set A with elements 1, 2, 3, 4, and 5, and set B with elements 2, 4, 6, 8, and 10. So we simply identify the common element of the two. So 2 is a common element as well as 4. That is then the that is then the intersection of set A and set B. So 2 and 4. This is the Venn diagram for intersection. So this is the intersection of set A and set B, this part. Okay. Here are more examples. Again, we are given set A with elements 1, 3, 5, 7, 9, set B with elements 2, 4, 6, 8, and set C with elements 1, 2, 3, 4, 5, and 6. We are going to find number 1, the intersection of set A and set B. The common elements of A and B are, do we have any? We do not have any. That's why for number 1, the answer is an empty set or null set. For number 2, we have the intersection of set B and set C, and the common elements of B and C are 2, 4, and 6. The answer here should be 2, 4, 6. Okay, and we've got the correct answer. This is the solution. Next, for number 3, the intersection of set C and set A. So they both have 1, they both have 3, they both have 5, and that's it. We have 1, 3, and 5 as the intersection of set C and set A. Okay, again, that should be 3. 1, 1, 3, and 5. This should be 3. I'll rewrite it. So we have C intersection A is 1, 3, and 5. This is the correct answer. Okay. And the next one, the next set operation is complement of a set. The complement of the set A, written as A prime, that is read as A prime, or complement of A, is the set of elements in the universal set U that do not belong to set A. Remember, let us first define what is a universal set. So a universal set is the set containing all elements under consideration. Okay, so it contains the overall number or all of the elements that we are considering in a case, okay, or in a certain problem. Here it is. The universal set consisting of all the elements under consideration. Now we have here an example. We have set U with elements P, Q, R, S, T. Set A with elements Q and S. For us to get the element of A prime or complement of A, we simply remove the elements of set A in U. When we remove Q and S, what is left is PRT, so that is the complement of set A. And when we draw a Venn diagram using when we draw a Venn diagram to show complement of a set, we simply shade the area outside of circle A, and that the shaded part contains the elements of A prime, or the complement of set A. Here are more examples. So we have here set U with elements 1 to 10, set A with elements 1, 3, 5, 7, 9, set B with elements 2, 4, 6, 8, set C with elements 1, 2, 3, 4, 5, and 6. So we are going to get the complement of all of this three items. So the first one, A prime, this is our solution. We are just going to remove 1, 3, 5, 7, and 9. And what is left is 2, 4, 6, 8, and 10. So that is A prime. Number 2, so we are again going to remove 2, 4, 6, 8. And what is left are the elements of A prime. We have 1, 3, 5, 7, 9, and 10. Lastly, number 3, C prime. We are going to remove 1, 2, 3, 4, 5, and 6 from the universal set, and we are left with 7, 8, 9, and 10. Those are the elements of C prime, or the complement of set C. So this should be C. We are getting the complement of set C. Now the fourth and last set operation is the difference of two sets. The difference of two sets A and B is the set whose elements belong to A but do not belong to set B. In symbols, the difference of A and B is A minus B, and the difference of B and A is B minus A. Here are some examples. So we have A minus B first. We are just going to remove the elements of set B from set A. And here is the solution. The elements of set B are set B are 1, 3, 5, 7, 9, and they both have 5 and 9 as a common element, so we are going to remove that from set A, and what is left in set A is 2, 8, and 10. That's why the answer here is 2, 8, and 10. For number 2, we have B minus A. We are going to remove the common element from set B. So remove 5 and 9, and we are left with 1, 3, and 7. Are you ready for the next lesson? Okay. This time we are going to solve problems involving sets using Venn diagrams. A while ago you have seen the Venn diagrams for union, intersection, and complement. First, let us define what is a Venn diagram. A Venn diagram is a diagram used to illustrate the relationship among sets. A particular set may be highlighted by shading the regions containing the elements of the set. So we have here an illustrative example. Okay, so first, for us to have or shade set A, okay, we have here a box first. Okay, this box contains all of the elements of set U. That's why we have here a letter U that is for universal set. As we have said earlier, a universal set contains all of the elements under consideration. So this box is very important. Now, we have here two circles, A representing set A and B representing set B. Now this time we are just going to shade first A. Okay, so to do that, let me change my pen first, and we are going to shade. Okay, so we are just going to shade circle A. That's it, and that The shaded part contains the elements of set A. Okay, when we shade it properly, this is how it will look like. Next, for set B, this time we are just going to shade B. There you go. So again, that shaded part contains all the elements of set B. And we shade it carefully. That is how it will look like. Number 3, this time we're going to shade A union with B. So let me use this color to show A, and then another color to show B. Since we are talking about union, so all of the shaded part is consider the union of A and B. That's why when we color it carefully, this is how A union B looks like. Okay, so all of it will be shaded all together. Number 4, this time the intersection of set A and set B. So let us see again. This is set A, and then we have set B. Since we are talking about the intersection, we just have to identify the part wherein the markings for A and B intersected, and this is where they both intersected. So this is where the intersection of set A and set B is. Okay, and here is a clear illustration of A union, A intersection with B. Number 5, A prime or A complement. So we're just going to remove all of the elements of set A from set U. We shade only the outside part and do not include circle A. Okay, we exclude circle A. Okay, let's shade it. Okay, you can use a crayon to color the outside part excluding A. When we do that, this is how it should look like. Number 6, we have B prime or the complement of set B. Again, we shade the outside part of set B. We shade all of the diagram except circle B. It means that all of the numbers or elements outside circle B are included in A prime or A complement. So again, when we shade that carefully, this is how it will look like. Next, number 7, A minus B. So this is set A, or this is circle A. We will just remove the area wherein circle B touches. Okay, when we do that, we are just going to shade this part. There you go. So we will only consider this part, and that is how it should look like if we color it carefully or shade it carefully. Number 8, B minus A. So we are going to shade the area of set B, but we will remove the area of part or circle A or set A. So this is it. There you go. Shaded region. Number 9, the complement of the union of set A and set B. Remember a while ago, the union of set A and B have set circle A and circle B as its shaded part. So we reverse that. Instead of shading the inside of the two circles, we are going to shade outside. So we are going to shade the outside part of the two circles. So the elements of the complement of the union of set A and B are all located outside. Okay, and that is how it looks like if we shade it. Next, number 10. This time the intersection or the complement of the intersection of set A and set B. And a while ago, the shaded part for the intersection is this part, the center, right? The middle part of A and B. But this time the complement is the part that is not shaded a while ago. Here we go. We are going to shade this area. So this is a shaded part. There you go. All of these, the ones I'm putting line, are shaded or will be shaded. Okay, let me just color it that way, and that is how it will look like if we finish shading all of those areas. Now we have here another section. In this section, we will understand how we can use Venn diagram in solving worded problems from real life situations. Given two sets, so this is how we can put numbers to indicate the parts of the Venn diagram. So we have part 1, part 2, and part 3. And then part 4 is outside. Okay. Now, how about if there are 3 circles? There you go. So we have 8 parts if there are 3 sets involved in a worded problem. So let's try to solve some examples. For example 1, a group of 40 students were asked whether they use either Twitter or Facebook or both. 23 of the students use Facebook and 25 use Twitter. Here are the questions that we will answer. How many use Facebook only? How many use Twitter only? And how many use both Facebook and Twitter? Okay, just like what we've learned a while ago. So we represent those two sets using circles. The first circle is for Facebook, and the second circle is for Twitter. So this is the area of the intersection of Facebook or number of students who uses Facebook and Twitter. Okay, so based on the given, the number of Facebook users is 23, so that includes the whole circle for Facebook. And then the number of those students who uses Twitter is 25. Now they have an intersection here. How do we get the value of that? So we need to find the intersection, then subtract the sum to the total number of students. So we have 23 plus 25, that is the sum of all of it. But we need to subtract the total from, or we subtract the total from this sum. So 48 is the sum of all of the Facebook users and Twitter users. And then we subtract 40, that is the total, and the result is 8. It means that there are 8 students who uses both Facebook and Twitter. Okay, if that is 8, Then we can have the value of the number of students who uses Facebook only by deducting the common or the intersection of the two. So we have 23, the total number of Facebook users, minus 8. This is the number of students who use both. Okay, and the result is 15. The same for Twitter. So we subtract 8 as well. 25 minus 8 is 17. So when we answer, here is example number 2. So the problem is red eyes. 550 students were enrolled for the school year 2020 to 2021 online classes due to pandemic. 170 of them enrolled in math class, 211 enrolled in science class, 224 enrolled in English class, 39 enrolled for both math and science, 40 enrolled for both math and English, 56 enrolled in both science and English, and 21 students enrolled in 3 subjects. Here are the questions that we will answer. How many students are enrolled in math only? How many students are enrolled in science only? How about for English only? And for the last question, how many students will not be taking up any of the 3 subjects? So we start, or it is easier for us to solve this if we are going to represent the numbers given using symbols. Okay, so the cardinality of set U, it means all of the students involved is 550, so that is how we will denote it. Next, number of math class, so we can use n of m is equal to 170. The same for science, we use letter S, so the cardinality of set S is 211. The cardinality of set E for English is 224, and the cardinality of, well, it says they're both, it means that is the intersection of math and science. So M and S, that is 39, and then the intersection of math and English is 40, science and English is 39. No, that should be 56. Okay, let me remove that. This should be 56. And then 21 students enrolled in 3 subjects. Okay, to denote that, we use this. So the intersection of math, science, and English is equal to 21. And that is how it looks like. We first identify, or we first find the area of intersection of the 3 circles, and based on the given, there are 21 of them. That's why we have here 21. Next, again, let me change this into 56. So we are done with 21. This time we have put 35 here, because based on the given, the number of students who uses or who enrolled in science and English is 56. But since there is a 21 here, and there are 21 students who enrolled in the 3 subjects, so we only need 35 more students to fill in this area, the intersection of a circle S and circle E. The same for the intersection of math and English. It says there 40, but since we already have 21 students, so we need how many more? We need 18 more. Okay, so again, this is 56 and 18 for us to get a total of 39. And then next, we need there are 224 enrolled in English class, so we need to find the number, okay, that we need to complete the 224 enrollees in English. We already have 19, we already have 21 and 35. So what is, or how many do, or what is the difference between 224 and these three numbers. That will be the next number that we will get. And when we solve for that, the answer is 149. So 224 minus the sum of these three numbers, 19, 21, and 35. The result is 149. Next, so we are done with the English class. We are done with this. Again, this is 56. Next, to get the number of students who enrolled in science only, of course, we subtract 2011 minus the sum of these three, 18, 21, and 35. When we do that, the result is 137. Okay, that means 137 enrolled in science only. And lastly, for math, there are 170, but we already have an 18 here, 21, and 19. So subtract that from 170, and the result is 112. Now we are done with our Venn diagram. Those are the important numbers. But when we add all of this, okay, the numbers 112, 18, 21, 19, 137, 35, and 149, the result is 491. But it says in the problem that there are 550 students. It means that out of the 550 students, 491 enrolled in these three subjects, and there are 59 who did not enroll in any of those three subjects. That's why we have here an outside part. We write 59. Okay, 59. Now we can answer our the questions a while ago. So students who are enrolled in math only, this is the answer, 112. Students who are enrolled in science only, 137. English only, 149. And those who will not be taking up any is the number outside, which is 59. So 59 is the answer to letter B. So that is the solution for example number 2. Here are some exercises that you can answer. Okay, to recap with our lesson for today. Okay, so we have here the universal set U with elements 1 to 10, A 1 to 5, set B with elements 2, 4, 6, 8, and 10, and set C with elements 2, 5, 7, 8, and 10. Let us answer number 1, the union of set A and set B. To get the answer to that, we simply combine the elements. So we have 1, 2, let us arrange it in increasing order. So 3, 4, 5, 6, 8, and 10. So that is the union of set A and set B. For the union of set A and set C, so again we have 1, 2, 3, 4, 5, 7, 8, and 10. Next, the union of set B and set C. The lowest number is 2, followed by 4, followed by 5, 4, 5, and then 6, 7, 8, and 10. So that those are the elements of the union of set B and set C. Next, intersection of set A and set B. The common elements are 2, what else? 4, and that's it. So the answer to number 4 is 2 and 4. Number 5, the intersection of A and C. They both have 2 and 2 and 5. So the answer here is 2 and 5. Next, the intersection of set B and set C, we have 2, and then 8, and then 10. Number 7, A prime, we are going to remove the elements of set A from U, and what is left is 6, 7, 8, 9, and 10. For number 8, we are going to remove 2, 4, 6, 8, 10 from U, and we are left with 1, 3, 5, 7, 9. A minus B, remove the elements of set B from A, so we will remove 2 and 4. We are left with 1, 3, and 5. Number 10, B minus C, remove the elements of set C, so remove 2, remove 8, remove 10. We are left with 4 and 6. That is the answer to numbers 1 to 10. Next, using the Venn diagram, illustrate each of the following sets. Okay, we already know that for number 1, we just shade circles X and Y, and that represents the union of set X and Y. Number 2, the complement of set X, so we shade everything except the inside of circle X. Okay. There you go. Okay, next, X minus Y, we are going to remove the elements of set Y from X, and we are left with only this. Okay, this is the diagram. This part is the shaded part. Next, number 4, Y minus X. Of course, we only shade Y, and we remove the area of X, set X. And then the intersection of X, Y, and Z is this part. This is where the 3 sets meet. Next, we have here a problem. 330 students were asked which fast food restaurant they have been to this year. The results of the survey were as follows. 8 have been all to 3, 18 have been to Jollibee and McDonald's, 21 have been to Mang Inasal and Jollibee, 20 have been to both McDonald's and Mang Inasal, 106 have been to Jollibee, 93 have been to McDonald's, 136 have been to Mang Inasal. First, we create a Venn diagram and then answer these questions. How many did not go to any of the 3? How many have been to Jollibee but not McDonald's? And how many have been to both Jollibee and McDonald's but not Inasal? So let us answer that first by filling in these circles with the proper numbers based on the given. Okay, so we have this circle J for Jollibee, MC for McDo, and MI for Mang Inasal. First, we find the number of the intersection of those 3. So we have there 8. So this is the intersection of the 3. Let me write that. Okay, so this is 8. Next, we have the next given is the intersection of students who went to Jollibee and McDonald's, and that is 18. So Jollibee and McDonald's, the total of this part should be 18. But we already have an 8 here. That's why the number that we need to complete 18 is 10. So now we have 18. Next, 21 have been to both Mang Inasal and Jollibee. So this area, we are referring to this area. And we already have an 8. So what we need to get a total of 21, subtract 21 minus 8, and the result is 13. That means there are 13 students here. Next, we have 20 have been to both McDonald's and Mang Inasal. So McDonald's and Mang Inasal, the total should be 20. We already have 8. So 20 minus 8, we have 12. Next, 106 have been to Jollibee. So if there are 106 who have been to Jollibee, we already have 10. We have 8 and 13. So 10 plus 8 is 18 plus 13. That is 31. We subtract it from 106. Okay, so we have 5, and then 10 minus 3 is 7. It means that there are 75 students who belongs to this area. Next, 93 have been to McDonald's. So 93, we already have 10 and then 8, so that is 18 plus 12, so that is 30. So 93 minus 30 is 63. It means that there are 63 students who belongs to this part. Next, 136 have been to Mang Inasal. Again, we already have 13, 8. So 13 plus 8 is that 13 plus 8 is 21 plus 12, that is 33. So we subtract that from 136 minus 33, so we have 103. There are 103 students in this area. Now let's continue. So take note of those numbers: 75, 10, 63, 75, 10, 63. Okay, so we create a Venn diagram to model the information. Okay, by the way, there are 46 when we add all of these numbers. So there are 46 46 students left. Okay, and they did not go to any of those 3 restaurants. That's why there are 46 in this outside those 3 circles. Now we are done with this. Let us answer the questions. How many did not go to any of the 3? Of course, the answer is 46. Number or letter C. How many have been to Jollibee but not McDonald's? So we are going to remove this area. Only Jollibee. Okay, so Jollibee area is this part. We are going to remove this part, this circle, including McDonald's. So we will only add 75 and 13. So 75 plus 13, Jollibee, but not McDonald's. So 75 plus 13 is how many? 88. So the answer here is 88. Next, for letter D, how many have been to both Jollibee and McDonald's, but again, how many have been to both Jollibee and McDonald's, but not Mang Inasal? So to answer that, we are just going to include or look at the diagram. So we are referring to the area, this area. So Jollibee and McDonald's, this is their intersection. This part, Jollibee and McDonald's, but excluding Mang Inasal. So we are going to remove 8. So we only have 10. The answer to this is 10. Okay, to the last question. That should be 10. Okay, so those are the answers to the question for this problem, worded problem. Okay, and that's it for our lesson. Thank you so much for listening. So our next lesson will be on the absolute value of a number. I hope that you continue listening and watching the videos that I'm posting. Thank you and goodbye. Hello once again, dear students. Today we are going to learn about the absolute value of a number, which is the third lesson in Mathematics 7. Once again, this is teacher Mary Jane, and I hope that you can learn from our discussion for today. Now, the absolute value of a number again, it refers to the distance of a number from 0. If we have here a number line, so we are already having here numbers, okay? So in a number line, we have the number 0 in the middle. Okay, as you can see, it has no sign because 0 is neither positive nor negative. Neither positive nor negative, so it has no sign. And then on its right are the positive integers, and to the left are the negative integers. Okay, and this number line has an arrowhead, meaning that there are more numbers that follows after negative 10. The same here, so we have an arrowhead here, meaning that there are more number that follows after positive 10. Now, if we have a vertical number line, we have again 0 in the middle, and then below it are the negative numbers, and above are the positive numbers or integers, since we are still dealing with integers, or we will deal with integers, so you can see whole numbers in this number line. And we have here an example on how to get the absolute value of a number. So when we are given this type of a problem, okay, we have here two bars, this bar and this bar. So that is read as the absolute value of -6. That means that we are looking for the distance of -6 from 0. And to do that, we just have to count the distance. We may start from -6 or we can start from 0. Anyway, we will have the same result. So I'm going to count now. So we have 1, 2, 3, 4, 5, and 6. So the distance of -6 from 0 is 6. So it is 6 steps or 6 blocks away from 0. That's why the absolute value of -6 is +6. Another example, example number 2, the absolute value of 6 is +6. Let us check. So 1, 2, 3, 4, 5, 6. So again, +6 is 6 blocks away from 0. So the absolute value of 6 is +6. Example number 3, the absolute value of +3 is 3. How did we get that? Simply count the distance between the two. So we have 1, 2, and 3. Okay, so you can see the pattern, right? You just have to, the easiest way to answer is for you to just remove the negative or the positive sign, because as we have said earlier, absolute value is always positive. Here is another example. So the absolute value of +9 is 9, so we have no problem here. The distance of +9 from 0 is 9. Number 5, -5, or the absolute value of -5 is +5, since the distance of -5 from 0 is again 5 units, so 5. Another example, the absolute value of -4 is 4, +4. And then number 7, we have here the negative. Okay, take note of this. The negative sign is outside the absolute value. So we read that as negative, the absolute value of 9. So we know that the absolute value of 9 is 9, but since 9, the negative sign is not included inside the absolute value symbol, so we include -9, okay, or the negative sign. That's why the answer to number 7 is -9. Okay, so that is the solution, -9. Number 8, so again, we have a negative symbol. We have a negative symbol outside the absolute value symbol. So we have here the negative of the absolute value of -5. The absolute value of -5 is +5. So that should be positive. Let me check that. Okay, so that is +5. And then we have a negative symbol outside. Negative times positive is positive. Negative times positive is negative. So this is -5. So the answer to problem number 8 is -5. -5. Okay, I hope that you were able to get how to solve for the absolute value of a number based on these examples. So take note that if there is a negative symbol outside the negative sign outside the absolute value symbol, then the result or the final answer is negative. Now let us have a real life example that we can solve using absolute value of a number. Okay. So we have here the municipalities of Tarlac province. Okay, so we have five. How many? 1, 2, 3, 4, 5, 6, 7. Okay, so it says there, suppose that the number line represents MacArthur Highway and the distance between each line is approximately 5 kilometers. So we are going to answer some problems regarding this number line. Okay, so we have these municipalities: Bamban, Capas, Tarlac City, Herona, Paniqui, Moncada, and San Manuel. Okay, so this number line is a highway, the MacArthur Highway, supposedly. And then the distance between each line is 5 kilometers. So it means that the distance between these two lines is 5 kilometers. This is another 5 kilometers from this line to this line. Okay, let us try to answer some questions about this number line. So number one, how far is San Manuel from Bamban? Okay, so we are referring to the distance of one place to another. So San Manuel to Bamban. So we have here San Manuel, and this is Bamban. So we just have to count the distance between these two places. Okay, so we start from San Manuel. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So that is 13 lines, 13 units away from San Manuel, from San Manuel to Bamban. So 13, but it says here one line, or the distance between the two lines, is 5 kilometers. It means that we just have to multiply 13 times 5. That's why the result, or the answer to number 1, is 65. So we just have to multiply 13 times 5 kilometers. No, so we have 65 kilometers. So that's the distance from San Manuel to Bamban, approximately. Okay, approximately. Number 2, what is the distance between Moncada and Tarlac City? Again, we count the distance, or the number of units. From Moncada, we start from Moncada and then Tarlac City. So we have 1, 2, 3, 4, 5, 6, and 7. That is 7 units away. So we multiply 7 times 5 kilometers. So we have 35 kilometers. So that is the approximate distance between Moncada and Tarlac City. Now let us check your understanding of our lesson as you answer the following. So I will give you a few minutes to try to solve or answer this on your paper, and then we will answer together. All right, I think you have your answer now. So for number 1, the absolute value of 9 is 9. The absolute value of -2 is 2. Number 3, the absolute value of 4 is 4. The negative of the absolute value of -3 is -3. Number 5, the absolute value of -4 is 4. Number 6, the negative of the absolute value of 19 is -19. For number 7, since it has a negative sign outside, so that is -11. Number 8, that is positive 16. Number 9, 9 plus 2 is 11, and the absolute value of 11 is positive 11. Number 10, 2 plus 3 is 5, and the absolute value of 5 is, of course, 5. So that is the answer of this or to this activity. Did you get it all? Good job if you got it correctly. Okay, so here are the answers once again. So we have here another problem. So suppose the MRT station from Pasay City to Quezon City were on a straight line and were 500 meters apart from each other. Let us try to answer the questions that follow. So number 1, how far would be the distance from Ayala? So this is Ayala to Ortigas. So let us just count the distance between the two places. So we have 1, 2, 3, 4, and 5. That is 5 units away. But it says in the given that each line or the distance between the two lines is 500 meters. So we multiply 500 meters. The result is 2,500 meters, or in kilometers, that is 2.5 kilometers. For number 2, what if Anna took the MRT from Kamuning and got off at Ortigas? So we have here, where is Kamuning? Okay, so we have Kamuning going to Ortigas again. How far would she have traveled? So we are going to count 1, 2, 3. That is 3 units away. We multiply 500 meters. So that is 1,500 meters, or in kilometers, 1.5 kilometers. Number 3, which station is farther from Santolan? Let's use another ink. So we have Santolan. This is our starting point. Quezon Avenue or Shaw Boulevard. So where is Quezon Avenue? This is Shaw Boulevard, and we have Quezon Avenue. Okay, so the distance between Santolan and Shaw Boulevard is 2 units. On the other hand, from Santolan to Quezon Avenue is 3 units. So to answer number 3, which station is farther? So Quezon Avenue is farther. Okay, Quezon Avenue. Number 4, which station is 1,500 meters apart to the east of Shaw Boulevard? So we have Shaw Boulevard, and the east is going to the, or it's right. So 1,500 meters away, that is 3 blocks or 3 units away, 1, 2, and 3. So it is this area or this place. That is Araneta Center or Araneta Center, Cubao. And for the last question, how far would be the distance from Magallanes to Quezon Avenue. Magallanes to Quezon Avenue. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So that is 10 units away times 500 meters. So that is equal to 5,000 meters or 5 kilometers. So those are the answers to this problem. The focus of our lesson for today is the most essential learning competency. That is for you, dear learners, to perform the fundamental operations on integers. As for the reference, we will be using the Compendium of Notes in Mathematics 7 by the Schools Division of Tarlac Province. Let us begin by defining what integers are. Do you have any idea what integers are? Now that we have defined what integers are, let us try to solve problems involving the fundamental operations. I want you to observe the examples and see or formulate the rules that we can follow in adding integers. For the first example, we have positive 27 plus positive 12. And for the solution, we are adding the absolute value of 27 and the absolute value of 12. As we add that, the result is the absolute value of 39. And we know based on our previous lesson that the absolute value of 39 is positive 39. For the next example, we are adding two negative integers. Negative 20 plus negative 15. For the solution, we are adding the absolute value or the negative, and then we have annexed the negative sign and then added the absolute value of our addends, 20 and 15. When we add that, we will come up with 35, but we still have the negative sign outside our parentheses. And using our rules in absolute value, since the negative sign is outside our bars, so the answer is negative 35. With that, what did you observe when we are adding integers with the same signs? For example, A, they are both positive. For letter B, they are both negative. Okay, so if the integers have the same sign, just add the positive equivalents of the integers and attach the common sign to the result. That is our rule when adding integers with the same sign. To summarize, when we are adding a positive plus a positive integer, the sum or the sign of the sum is positive. Likewise, if we are adding a negative number to a negative number, the sum is negative. We just have to add our addends and annex the negative sign. Remember that for adding integers. Let's continue with these examples. This time we are going to add integers with the same or with different signs. We are adding 38 or positive 38 and negative 20. Let's look at the solution. So it says there, get the difference between 38 and 20. The result is 18. And since 38 is greater than 20, the sign of the sum is positive. Hence, 38 plus negative 20 is equal to 18. Given that example, can you give a rule that we can follow in adding integers with different signs? What operation are we applying? That's right. If the integers have different signs, get the difference, or we subtract the numbers, and then attach the sign of the larger number to the result. In short, when we are adding a positive and a negative number, we have to subtract their positive equivalents and then get the sign of the larger number. So that applies if we are adding negative and a positive integer. Here is another example when we are adding a negative and a positive integer. So for the solution, since they have different signs, 42 and 16 will be subtracted and their difference is 26. And since 42 is larger and its sign is negative, so the sum is negative 26. Let us continue with the rule in subtracting integers. In subtracting integers, we follow this rule. Add the negative of the subtrahend to the minuend. For example, 10 minus 6 is equal to 10 plus negative 6. What did you observe? We have changed our operation into addition and then change our subtrahend with its opposite. Since in our original problem we have positive 6, it will be changed into negative 6. That's why we can rewrite 10 minus 6 as 10 plus negative 6. And we can apply our rule a while ago in adding integers with different signs. And when we add those two, we will just subtract 10 and 6. So 10 minus 6 is equal to 4. Since the sign of the larger number 10 is positive, our answer is positive. For example B, we have 15 minus negative 8. That is equal to 15 plus 8. How did we get that? Again, our operation will be changed into addition. And our subtrahend, or the sign of our subtrahend, will be changed into its opposite, which is positive. That's why we had 15 plus positive 8, or simply 15 plus 8. And the sum of those two is 23. That's why the answer for example B is positive 23. Let's move on to the next example. We have negative 3 minus the quantity negative 2. On the right side of the equation, we have negative 3 plus 2. How did we get that? We got that by changing our operation to addition and then changing the sign of the subtrahend with its opposite, which is positive. And applying the rule in adding integers, negative 3 plus 2 is equal to negative 1. Next, negative 4 minus 15 is equal to negative 4 plus the quantity negative 15. And applying the rule in adding integers with the same signs, we add 4 and 15. That is 19, and since they are both negative, so the sign of our sum is negative.
We can also use sign tiles to add and subtract integers. So here are some examples. For number 1, if we are given 10 plus 2, So we are going to draw tiles. Okay. So for positive 10, we are going to draw 10 tiles showing the positive sign. So that is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And for positive 2, we are also going to draw 2 tiles with the positive sign on it. Now, if that is the case, simply add all of the tiles with the positive sign. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So the answer here is 12, and since all of the tiles are positive, so it is positive 12. And when the sign is positive, we don't have to write it before the number. Okay, so simply 12 or positive 12 is the answer in number 1. For number 2, we are given the problem 3 plus negative 2. So again, we represent first 3 as using 3 tiles, or 3 tiles with the positive sign on it. So we have 1, 2, and then 3. Okay, for the negative number, let me use another ink. So let's use purple. This time we are going to put the negative sign on the tile. So we have negative, and since we know that positive plus negative is equal to 0, so let us try to match the tiles so that we'll have zeros. Okay, so this tile and this tile, when we combine them, it is 0, so we will cross it out. And then another one, this tile and this tile, we are going to cancel it. Okay, so based on that, the sum of this is based on the remaining tile. So we only have one tile, so that is 1, and the sign of the tile is positive. It means that the answer here is positive 1, or simply 1. So 3 plus negative 2 is equal to 1. For number 3, so again we use the purple ink for negative 5. So I am going to draw 5 tiles. So 1, 2, 3, 4, and 5 with the negative sign on them. And then to represent positive 16, let us use blue ink. So I'm going to draw 16 tiles with positive sign on it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So let us put the positive sign on each tile. There you go, and then we can cancel the pairs, positive and negative tiles, so that is equal to 0. Okay, cancel, cancel these two, cancel, 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 and then counting the number of tiles left, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and all of the tiles are positive, so our answer here is positive 11. For number 4,
we have negative 9. First, let us draw 9 tiles with negative sign on them. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. So they are all negative. After that, we can withdraw one tile with a positive sign. We can cancel a pair of negative and positive tile, so we can cancel this, and we are left with how many tiles? We are left with 1, 2, 3, 4, 5, 6, 7, 8. And what is the sign of those tiles? Yes, they are all negative, so the sign of our answer, or the sum of negative 9 and positive 1, is negative 8. Next, number 5. So we have a positive number here, so positive 6. We will draw 6 positive tiles. So 1, 2, 3, 4, 5, and 6. And then let us put the positive sign. There you go. And then for negative 7, we have 1, 2, 3, 4, 5, 6, and 7. So that is, or they are all negative. And then we cancel the pairs. So one, we can cancel this, this, and this. So we are only left with this tile, and there's only one. Its sign is negative. So the sum of positive 6 and negative 7 is negative 1. Another example. So this time we have negative 2. So let's use a purple ink. Negative 2, that means 2 negative tiles. And then positive 2, that we will draw 2 positive tiles. And then we cancel the pairs. Okay, so we are left with no tile at all, so the answer here is 0. Of course, you already know that 0 is neither positive nor negative, so just 0. Number 7, negative 4 plus negative 6. So we represent negative 4 using 4 negative tiles. 1, 2, 3, and 4. So those are all negative. And then negative 6, we are going to draw 6 tiles that are negative. 4, 5, and 6. All right, now there is no positive tile, so we are going to count how many tiles are there in all. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we have 10 tiles, but those tiles are all negative. So the sum of negative 4 and negative 6 is negative 10. Number 8. This time we have 2 positive numbers. So let us draw 7 tiles first. Positive tiles 3, 4, 5, 6, and 7. So they are all positive. And we are going to add 4 more for the addend. Okay, so 1, 2, 3, and 4. Again, we cannot cancel any pair, so we simply count the number of tiles, and there are 11. And since they are all positive, so that is the final answer. The sum of 7 and 4 is 11. Next, negative 9 plus negative 3.
So they are negative. We are going to draw 9 negative tiles 2, 3, 4, 5, 6, 7, 8, and 9. So that is negative. Next, we are going to draw 3 negative tiles 1, 2, and 3. And of course, we are going to count all of them since we cannot cancel any pair. So that there are 12 tiles and they are all negative. So the sum of negative 9 and negative 3 is negative 12. And for the last example, we have negative 3 plus negative 3. So they are both negative. So you have 1, 2, and 3. That is for this one. And then another 3 negative tiles. So we have 1, 2, and 3. We cannot cancel any. So simply count all of them. And there are 6 tiles which are all negative. That means that the answer to number 10 is negative 6. Now, how about for subtraction? So let us look at the examples for. Alright, so for subtraction, of course, we have to follow the first step before we draw tiles. So our step again in subtracting is for us to change the sign of our subtrahend as well as the operation. Okay, so for number 1, we are going to change this. Okay, let me rewrite that. So we have 10, and then our operation will become positive, and then we take the opposite of negative 2. So we have um, again we take the opposite of positive 2, so that is negative 2. Okay, and then we can apply or we can draw tiles representing this number and this number. Okay, so for positive 10, we are going to draw 10 tiles that are positive. So 3, 4, 5, 6, 7, 8, 9, and 10. So they are all positive. And then we are going to draw 2 tiles that are negative. So we have 1 and 2. And of course, we will cancel what we can cancel. So we can cancel this pair and this pair. And if we are going to count the number of tiles left, we have 8, and that is, they are all positive. So our answer is positive 8. For number 2, we have this. So again, let me change first the operation as well as the sign of the subtrahend. So we have 3, and then our operation will become positive, and then the sign, we get the opposite of the sign of the subtrahend. Since it is negative, so it will become positive 2. So even if we do not draw sign tiles, we know that the answer here is 5. But for the sake of an example, we are going to draw tiles. Okay, so for positive 3, we have 1, 2, and 3. So put the positive sign. And then for 2, we have 1 and 2. Adding all of those tiles, so we have 5 tiles that are all positive. So the sum of 3 or 3 minus negative 2 is equal to positive 5. Example number 3, so we have negative 5 minus 16. Let us rewrite it first. So the minuend is still the same, negative 5. Our operation will become addition, and then positive 16 will be negative 16. Now we can represent them using tiles. Let's first represent negative 5. So we have 1, 2, 3, 4, and 5 negative tiles. And then another 16. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So those are all negative. And counting them all, they're all of the tiles are negative. So we just count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and 21. So the result is 21 tiles that are negative. So negative 21. Simplifying negative 5 minus 16, the result is negative 21. Number 4, we have negative 9 minus 1. Again, let us rewrite it first. The minuend is still the same, so negative 9. And then this sign for the operation will be addition. And then we have a positive subtrahend, so it will become negative. Okay, now we can represent them using sign tiles. For negative 9, we have 1, 2, 3, 4, 5, 6, 7, 8, and 9. Next, negative 1. So let's draw one negative tile, and that's it. Counting all of them, so we have 10 negative tiles. So the answer here is negative 10. Number 5, let us rewrite it again. So we have positive 6. This will become addition since this subtrahend is negative, so it will become positive 7. So we have 6 plus 7, which is equal to 13. But again, for the sake of the example, so let us draw 6 positive tiles first. 2, 3, 4, 5, 6 for this. So let's put the positive sign. And then another 7 for the subtrahend, or for the addend. 1, 2, 3, 4, 5, 6, and 7. Counting all of those tiles, we have a total of 13 tiles that are positive. So we have positive 13. Next is number 6. Let's continue with example number 6. So we have negative 2 minus 2. Again, we're right. We copy the minuend negative 2, and then the operation will become addition, and positive 2 will become negative 2. And then we can use sign tiles. So negative 2 we have, let's draw 2 negative tiles and then another 2. Counting all of those, we have how many? We have 4 negative tiles, so that is negative 4 over 7. That can be written as negative 4 minus negative 6. So we have negative 4 plus positive 6. Okay, so let us represent negative 4 first. We have 4 negative tiles, 1, 2, 3, and 4. And then 6 positive tiles, 1, 2, 3, 4, 5, and 6. Again, we can cancel the pair. of negative and positive tiles. So cancel, 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 cancel. And we are left with two tiles that are both negative. So the result is positive 2. Or negative 4 minus negative 6 is equal to positive 2. Number 8, we have 7 minus 4. We can rewrite it as 7 plus negative 4. Okay, so we represent 7 first using 7 positive tiles. 2, 3, 4, 5, 6, 7. And then negative 4 can be written as negative 4 negative tiles. And we can cancel some pairs. Cancel, 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 cancel. And we are left with 3 tiles that are positive. So we have positive 3 as the answer in number 8. Number 9, we have negative 9 minus negative 3. We have negative 9. It will become addition. And then negative 3 will become positive 3. And then we use sign tiles. First, we use sign tiles for negative 9. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. There you go. And then for positive 3, let's draw 3 positive tiles. 1, 2, and 3. We can now cancel some pairs. So 1, 2, and 3. Now we count what is left. So we have 1, 2, 3, 4, 5, 6, 6 negative tiles. So the answer here is negative 6. And for the last example, again we rewrite it. So we have negative 3 plus 3. Okay, so negative 3 first. So let's draw 3 negative tiles. And then 3 positive tiles for the addend. So 1, 2, and 3. Cancel pairs of positive and negative tiles. So we cancel, cancel, cancel. There is no tile left. So we have 0. The answer to negative 3 minus negative 3 is 0. So I hope that through these examples you find it easier to add and subtract integers.
For multiplying integers, I will again show you examples and then try to observe as we come up with a rule that we can follow in multiplying integers. For example A, when we multiply positive 4 times positive 5, the result is positive 20. Example B, when we add negative 8, or when we multiply negative 8 times negative 9, the product is positive 72. And the rule that we follow is that if the integers have the same signs, their product is positive. Here is another example. 7 or positive 7 times 11 is equal to positive 77. With that, we can have this rule that when we multiply two positive integers, the product or the sign of the product is positive. Likewise, if we are multiplying two negative integers, their product or the sign of their product is also positive. Now, what if our multipliers have different signs? What will be the sign of our answer? Let's look at the next example. For example D, we will be multiplying negative 5 and positive 7. And the result here is negative 35. For example E, when we multiply positive 14 times negative 3, the result is negative 42. And when we multiply 20 times negative 6, the result is negative 120. What did you observe when we are multiplying integers with different signs? That is correct. If the integers have different signs, their product is negative. Or simply, positive times negative is negative, and negative times positive is negative. We move on to dividing integers. Again, I want you to observe the following examples and come up with rules that we can follow. For example A, when we divide positive 45 divided by positive 5, the result is positive 9. When we divide negative 81 divided by negative 9, the result is positive 9. And for example C, when we divide positive 77 divided by 11, the result is positive 7. What did you observe with the signs of our divisor and dividend? They are both, or they have the same signs. And what did you observe with our quotient? The sign of our quotient is all positive. With that, we come up with this rule that if the integers have the same signs, their quotient is positive. It means that the rule in multiplying and dividing integers are actually the same. Again, when we divide positive divided by a positive, the result or the sign of the quotient is positive. When we divide negative by a negative integer, the sign of the quotient is also positive. Now we have an idea about the rule that we follow in dividing integers with different signs. That is, when we divide positive by negative, the result or the sign of the quotient is negative. And when we divide negative by a positive, the sign is again negative. Here are some examples. When we divide negative 35 by positive 7, the result is negative 5. 16 divided by negative 2 is equal to negative 8. And negative 70 divided by 10 is negative 7. And 4 divided by negative 5 is equal to negative 4/5. But here is an exception. When we divide a number by 0, no matter what the divisor is or what the dividend is, as long as we divide it by 0, the result will always be undefined. Here is our rule that we follow again. If the integers have different signs, their quotient is negative. Now I want you to take note of those rules as we summarize using this song. Know, know, know your integers. You can sing this to the tune of Row, Row, Row Your Boat, or you can use other tunes to sing. Okay, here is the lyrics for the summary of our lesson. Same sign, add and keep. Different sign, subtract. Keep the sign of the bigger number, then it will be exact. That is the rule for adding integers. Now here is for subtraction. Change the minus to a plus. Change the sign of next. Then all you do is add them up as if it were a plus. And lastly, for multiplication and division, multiply or divide, it's an easy thought. Same signs are positive, different signs are not. Here are some of the real-life applications of our lesson for today. For problem number 1, Felix reported that the coldest day on record for his town was 5 times colder than yesterday's temperature, which is negative 4 degrees Celsius. What was the temperature of the coldest day on the record in Felix's town? To answer that, we just have to multiply 5 times negative 4, and the result is negative 20 degrees Celsius. For example number 2, there are 336 oranges in 12 baskets. How many oranges are there in 3 baskets? To answer this, we just have to divide 336 divided by 12, and the result is positive 28, or there are 28 oranges in each basket. And for number 3, a vendor gained 50 pesos on the first day, lost 28 pesos on the second day, and gained 49 on the third day. How much profit did the vendor gain in 3 days? For that, we can represent the gains as positive and the losses as negative. To come up with our equation, which is 50 plus 28, or plus negative 28 plus 49, to get the result, which is 71. Now, aside from these examples, there are more real-life applications of our lesson, which I want you to identify and list down in your notebook.
Okay, so let's check how well you've understood the lesson as you answer the following as fast as you can. Okay, so 25 plus 8, what do you think is the sum of 25 and 8? Okay, that's right. Since they are both positive, so the result is positive 33. So we simply add the numbers and then get the sum, which is 33. For example number 2, or for problem number 2, we have negative 6 and then positive 6. So what will you do if they are both, or if they have different signs? That's right. So we are going to subtract the numbers. So 6 minus 6 is equal to 0, and 0 has no sign. So the answer to number 2 is 0. Number 3, so we have two positive numbers. We simply add 14 and 25. The result is 39. Number 4, we have numbers with different signs. So again, we subtract them. 28 minus 23 is equal to 5. That's right. And since the larger number is positive, which is 28, so we have positive 5 as the answer. Number 6, again, they have different signs, so we subtract them first. 36 minus 16 is equal to 20. And since the larger number is 36 and its sign is negative, so the sign of the answer is negative. So we have negative 20. Number 6, we have 19 plus negative 16. Again, they have different signs, so you have to subtract 19 and 16. So 19 minus 16 is 3, and the larger number is positive, so the answer is positive 3. Number 7, we have negative 15 and negative 4. We again subtract 15 and 4, so 15 minus 4 is equal to 1, and the sign of the larger number 15 is negative, so we have negative 1 as the answer in number 7. Number 8, negative 12 plus negative 12, they are both negative, so we add them first. 12 plus 12 is 24, and then adding them, or both of their signs is negative, so we have a negative as an answer, negative 24. Number 9, again we have two negative numbers, so add 24 and 16, the result is 40, and then copy the sign, which is negative. So the answer is negative 40. For number 10, negative 13 and negative 19. So we have negative 32 as the answer. Okay, continue. So we have subtraction this time. So the first step that you can do here is to change the operation into addition. So let me use another ink for that. So this will be addition. Okay, plus addition, and then reverse or use the opposite of the subtrahend. Okay, so that is positive 11, it will become negative 11. 16 will become negative 16, 45 will be negative 45, 22 will be negative 22, 30, negative 30 will be positive 30, and then negative 19 will be positive 19, and then positive 18 will be negative 18, negative 10 will be positive 10, negative 18 will be positive 18, and negative 25 will be positive 25. To have a clearer view of the problem, so let us rewrite them. So number 16, we have 25 plus negative 11. Number 17, we have negative 2 plus negative 16. Number 18, we have 15 plus negative 45. Number 19, negative 11 plus negative 22. So we have negative 11 plus negative 22. Number 20, we have 12 plus 30. Number 21, 22 plus 19. 22, we have negative 13 plus negative 18. Number 23, we have negative 10 plus 10. Number 24, we have negative 20 plus 18. And 25, we have negative 15 plus 25. And applying the rule in addition, for number 16, the answer is 14. Number 17, we have negative 18. Number 18, negative 30. Number 19, negative 33. Number 20, 42. 21, 41. Number 22, the result is negative 31. Number 23, we have 0. 24, negative 2. Number 25, we have positive 10. So those are the answers for these problems. That ends our lesson for the operations on integers. Our next lesson will be on the properties of the operations on integers. I hope that you check and watch the video for this lesson. Once again, this is teacher Mary Jane. Until next time, bye. Hello dear students, today we are going to learn about the different properties of the operations on integers. So I hope that you can still remember the rules on how to add, subtract, multiply, and divide integers. The integer properties will help us to simplify and solve a series of integers easily. And all properties and identities for addition, subtraction, multiplication, and division of numbers are applicable to all the integers. And if you can still recall, integers include the set of positive numbers, 0 and negative numbers, which can be represented with the letter Z. Okay, so that is our notation for integers. The first property of the operation on integer is the closure property. The closure property states that two integers that are added and multiplied remain as integers. When we add two integers, the result is still an integer. Okay, so it is closed under the set of integers. The set of integers is closed under addition, subtraction, and multiplication. So it does not include division because there are times when we divide numbers or divide integers and the result is a fraction or a decimal. So it does not belong to the set of integers. Okay, so we have here an example. So notations. For instance, if A and B are elements of Z, so again, this is the symbol for element, right? So that means that A and B is an integer. Then we can say that A plus B is an element of Z, or an element of the set of integers. Okay, so here are some examples. So you have 2 plus 5 is equal to 7. So 2 here is an integer, a positive integer, and 5 is also a positive integer. When we add the two of them, the result is 7. So it is also an integer. 7 is also an integer. Okay, so it is closed under the set of integers. So that is what closure means. Another one, we have here another example. So we have negative 3 plus 11 is equal to negative 8. Negative 3 is a negative integer. Positive 11 is a negative or is a positive integer. And when we add them both, the result is also an integer. So again, this is an example showing the closure property of integers. The next one is for multiplication. So this means that when we multiply two integers, the result is also an integer or belongs to the set of integers. Okay, so we have example number 1. 4 times 5 is equal to 20. So we have 4 as an integer and 5 is also an integer. The result is also an integer. Another example, we have negative 3 times 9 and the result is negative 27, which is also an integer. Okay, now let me show you why sometimes or why multiple division is not closed, okay, or does not belong to the group. Okay, so when we divide 4 divided by 2, now this is for division. 4 is an integer, right? And 2 is also an integer. So dividing the 2, we have 4 divided by 2 is 2. So we have no problem here. What is this? The dividend is an integer, the divisor is also an integer, and the quotient is an integer. But how about if we have another example like this? So we have 3 divided by 2. Okay, so 3 divided by 2, they cannot be divided exactly by each other. So the result here is either 3 over 2 or 1.5 in decimal. Okay, so why uh, this is why division of integers is not closed under the set of integers. Okay, because 3 halves or 1.5 is not an integer, but they are rational numbers. Okay, rational numbers. So again, the closure property is only closed for addition, subtraction, and multiplication. So it cannot be for division because there are instances when we get an answer of a rational number instead of integers. Second property is on commutative or is called the commutative property. The commutative property states that changing the order, remember the word order, of two numbers that are either being added or multiplied does not change the value. So even if we change the order, it means that whichever number comes first, the result will always be the same. Okay, so in notation, if A and B are elements of set Z, or the set of integers, then we can say that A plus B is equal to B plus A. So this is for addition. Okay, this is for addition. We have here an example. So when we add 4 and 5, which are both integers, the result will always be the same, even if we change the order of our addends. So in the right-hand side of our equation, we have 5 plus 4. So 5 came first instead of 4, but still the result is the same, which is 9. So that is commutative property. Number 2, negative 3 plus 6. So we reorder or change the order. We write 6 first and then negative 3, but still the result here is the same, which is 3. So negative 3 plus 6 is 3, and 6 plus negative 3 is also 3. Okay, so that is for commutative property for addition of integers. And here is for multiplication. So we have A times B is equal to B times A. So for example, we have negative 3 times negative 4. Even if we change the order of these two numbers and write it as negative 4 times negative 3, the result negative 12 is still the same. So nothing will change when it comes to the product of those two numbers. Okay, and why is not subtraction included? So let us have an example for subtraction. Okay, so let's have 2 and 1. Okay, so when we subtract 2 minus 1, the result is 1. But when we subtract 1 minus 2, the result is negative 1. And 1 is not equal to negative 1. So this is a good example to show that this commutative property does not apply to subtraction. The same with division. Let's say, for example, 4 divided by 2. So 4 divided by 2 is equal to 2. But if we are going to reverse the numbers or change the order, having 2 divided by 4, the result here is 0.5 or 1/2. And these two are not equal, not equal. Okay, so it does not, since they're not equal, so we cannot say that, or we cannot say, we can say that they really do not belong to the operations covered by the commutative property. The third is the associative property. So the associative property states that changing the grouping, if what's this? The previous one, if commutative property is on the order of numbers, for associative property, it is on the grouping of numbers. Okay, so states that changing the grouping of numbers that are either being added or multiplied does not change its value. So again, it is solely for addition and multiplication, because there are instances when we subtract or when we divide and change the grouping, the result will be different. Okay, so we have here an example. So we have here on the left hand side, the group numbers are A and B. And then for the right hand side, what is grouped is B and C. Now let us change those letters or variables into numbers. So we have 1 plus 2 plus 3. That is for the left hand side, and for the right hand side we have 1 plus 2 plus 3, and the group numbers are 2 and 3. Now simplifying, so we have 1 plus 2 is equal to 3 plus 3, and then we have 1 plus 5 on the right hand side. Still the result is the same, which is positive 6. So changing the order of numbers being added does not change the value. Same for multiplication. Okay, so for multiplication, here is another example. So example number 2, we have negative 1 plus 2 plus 2. So what is grouped for the left hand side is negative 1 and 2, and then for the right hand side we have 2 plus 2. Okay, so even if we have different results here, plus 2 and negative 1 plus 4, the results are still the same, which is positive 3. And here is for multiplication. So A times B, the quantity times C is equal to A times the quantity B times C. Okay, so here is an example. So what is grouped on the left hand side is 2 and 5. On the right hand side we have 5 and 4. But still, when we simplify those numbers, the result is still the same, which is 40. And for example number 2, we have negative 3 times 4 times 5. So that is equal to negative 3 times the quantity 4 times 5. And both the result is both the results are the same, which is negative 60. The fourth property is the distributive property. So the distributive property states that when two numbers have been added or subtracted and then multiplied by a factor, the result will be the same when each number is multiplied by the factor and the products that are being added or subtracted. Again, we have here a notation. If A and B are elements of set Z or set of integers, then we can say that A times B, or A times the quantity B plus C, is equal to A times B plus A times C. We have only distributed A to these two numbers. Okay, so A times B and then A times C. So we have here an example. So if we have 4 times 2 times 3, it can be rewritten or it can be distributed. The factor 4 can be distributed among the two added. So we can pair up 4 and 2. We have 4 times 2. And then we can also pair up 4 and 3. So we have 4 times 3. Now we simplify first on the left hand side. So 4 times the group number is 2 and 3, so the result is 5. For the right hand side, 4 times 2 is equal to 8, and then 4 times 3 is equal to 12. Still, the result is the same, which is 20. Example number 2, so our factor here is negative 3. We multiply it to the two numbers or to the two addends. So negative 3 times 1 and then negative 3 times 2. Okay, we simplify the left hand side. So we have negative 3 times 3. For the right hand side, we have negative 3 plus 6, or negative 3 plus negative, this should be negative 6. And the result is the same, which is negative 9. The fifth property of the operation in integers is the identity property. Okay, first is the additive identity. So the additive identity states that the sum of any number and 0 is the given number. 0 is the additive identity. Okay, here is an example. So when we add a number by 0 or with 0, the result will always be the number itself. Here, for example, 2 plus 0 is equal to 2, 0 plus negative 3 is equal to negative 3, and negative 10 plus 0 is equal to negative 10. Another one, so we also have what we call the multiplicative identity. It states that the product of any number and 1 is a given number. So we call 1 as the multiplicative identity. And we know that when we multiply a number by 1, the result is always the number itself. Okay, so 5 times 1 is equal to 5. Number 2, 1 times negative 4 is equal to negative 4. And negative 12 times 1 is negative 12. And the sixth property is the inverse property. The first is the inverse property of addition. States that the sum of any number and its additive inverse is 0. The additive inverse of a number A is negative A. Now, if the given is a negative number, of course, its inverse or additive inverse is the positive number. Okay, here is an example. So when we add 4 and its additive inverse, which is negative 4, the result is 0. So the additive inverse of 4 is negative 4. Example number 2, negative 11 plus 11 is equal to 0. So again, we have here the inverses. The inverse of negative 11 is positive 11. And when we add both of them, the result is 0. So they are the additive inverse of each other. We have additive inverse, we also have our multiplicative inverse or reciprocal. Okay, the inverse property of multiplication states that the product of any number and its multiplicative inverse or reciprocal is 1. The multiplicative inverse of a number a is 1 over a. Now, for instance, we have, what's this? Let's take at the examples, okay, for us to understand it better. Now, if we have, for example, 4, its inverse is actually 1 over 4. So when we multiply 4 times 1/4, the result is 1. Because 4 is can be written as 4 over 1. And when we get the reciprocal, when we say reciprocal, we simply interchange the value of the numerator and the denominator. Okay, so since 1 is the denominator here, we move it as a numerator in our multiplier times 4. Okay, so this is the reciprocal of 4 over 1, or 4. Okay, and when we multiply them, the result is 1. Another example, so in negative 11, since it is negative, so its inverse is also negative, and then that is over 1. When we reverse it or get the reciprocal, we will have 11, or negative 1 over 11. Okay, and that is the multiplicative inverse or reciprocal of negative 11 is negative 1 over 11. Here is another one. So the reciprocal or multiplicative inverse of 6 is 1 over 6. Right. And then we also have, it was repeated. Okay, let us check if you were able to take note of all of those properties. So I have here a table showing a given, and then we are going to identify the property used. Okay, for number 1, 0 plus negative 3 is equal to negative 3. Since it is showing that when you add a number by 0, the result is the same number, so that is identity property or additive identity. Additive identity, since the operation is addition. Number 2, 2 times a quantity 3 minus 5 is equal to 2 times 3 minus 2 times 5. What is your answer? Okay, the answer is distributive property, because we have to distribute, or we have distributed the factor 2 with the numbers 3 and 5. Number 3, negative 6 plus negative 7 is equal to negative 7 plus negative 6. As you can see, we have changed or interchanged the order of the two addends, but still, when we simplify that, the answer is the same. What property is that? You're right, commutative property. Number 4, multiplying a number by 1 gives the number itself. So that is multiplicative identity. Number 4, we have negative 4 multiplied by 1/4, or negative 1/4. So the result is 1. Okay, negative 4 and negative 1/4 are inverse of each other. So this is multiplicative inverse. Multiplicative inverse. Number 6, 2 times the quantity 3 times 7 is equal to the quantity 2 times 3 times 7. That involves grouping, so that is associative property. Number 7, 10 plus negative 10, or its inverse, is equal to 0. That is additive inverse. Number 8, 2 times 5 is equal to 5 times 2. So we have just changed the order, but still the answer is the same. That is commutative property. Number 9, 1 times negative 1/4 is equal to negative 1/4. We are multiplying with the additive identity 1, so that is, or multiplicative identity. So we have multiplicative identity. And for number 10, we have negative 3 times the quantity 4 plus 9 is equal to negative 3 times 4 plus negative 3 times 9. We have just distributed negative 3, so we have distributive property for number 10. So those are the answers. And another one. Complete the equation below by filling out the blanks with a missing number. Then determine what property was used to solve each equation. Okay, so for number 1, negative 4 plus 4 is equal to 0. And what property is that? Additive inverse. Number 2, negative 6 plus 0 is equal to negative 6. We are adding with 0, which is the additive identity, so that is additive identity. Number 7, or number 3, 7 times blank is equal to 1. What will we multiply? Of course, its inverse, which is 1 over 7. So that is multiplicative inverse. Number 4, 6 times 7 times, or the quantity 6 times 7 times 8 is equal to 6 times the quantity blank times 8. So what is the missing number here? Of course, it is 7. And that involves grouping, so associative property. Number 5, negative 4 times blank is equal to negative 4. And the answer is 1. And that is identity property. Identity property, multiplicative, and identity, to be more specific. Number 6, we have negative 6 times 4 is equal to negative 24. And the result here is closure property. Number 7, the quantity 4 plus 5 plus 2 is equal to 4 plus the quantity 5 plus blank. And what is missing is 2. Am I right? Yes. And what property is being shown here? We have the grouping. It involves grouping, so that is associative property. Number 8, 2 over 5 times blank is equal to 1. So we just need the reciprocal of 2, 5, which is 5 over 2. That is, since it involves reciprocal, so that is multiplicative inverse. Number 9, blank plus 4 over 7 is equal to 0. So since the operation here is addition, we have to identify the additive inverse of 4, 7, and that is its opposite, which is negative 4 over 7. And what property is that? Additive identity, or additive inverse, I should say, because we are adding the number by its inverse to get the result, which is 0. For number 10, we have 3 times the quantity 4 minus 5 is equal to the quantity 3 times 4, quantity 3 times 4 minus 3 times blank. So what do you think is the missing number? The missing number here is 5. And since we have distributed 3 to these two numbers, of course, obviously, number 10 is a distributive property. Number 10 shows distributive property.
Alright, so those are some of the examples showing the different properties of equality. So again, let us recall what are those properties that we've learned. So we have closure property, additive identity, additive inverse, multiplicative inverse, multiplicative identity, associative property, what else? I think that's it. A distributive property. And I hope that you were able to answer all of those problems correctly. Okay, those are the answers. Let me just flash them, but we have already answered it previously. Okay, so please check the next lesson, which is rational numbers in different forms. Check my channel for the video of this lesson. So thank you so much for listening. Once again, this is teacher Mary Jane. Until next time, goodbye. Hello students, today we are going to learn a new lesson which is on rational numbers. So today we are going to learn about rational numbers in different forms. This is teacher Mary Jane and I hope that you listen as we discuss this lesson. Our most essential learning competency is for you learners to express rational numbers from fraction to decimal and vice versa. And that is our reference. This is our reference. Now let us define first what is a rational number. The word rational is derived from the word ratio. Okay, we have here the word ratio, which means quotient. So when we say quotient, that is the result when we divide two numbers. Okay, result when we divide numbers. So we have here another statement. Rational numbers are numbers which can be written as a quotient of two integers, a and b. Okay, so a and b can be any integer. Okay, so do you remember what integers are? Integer includes positive whole numbers. What else? Negative numbers, whole numbers, and of course 0. Okay, but we have here a condition that b or the divisor should not be equal to 0. Okay, because when that happens, the answer is undefined. Okay, let's say for example 1 is divided by 0, so the answer there or that is undefined. So if you're going to key that in your calculators, it will be syntax error. Okay, so take note of that. So that could be a positive, the numerator can be a positive number or a negative number or 0. It doesn't matter. But for the denominator, we cannot use or we cannot put 0 as a divisor. Here are some examples. So rational numbers are in different forms. So it can be an integer, okay, just like this number, because we can write 5 as a quotient of two numbers, namely 5 and 1. So when we divide 5 divided by 1, the result is 5. So 5 is an integer, 1 is also an integer. Another example, so we have 0. 0 can be written as a quotient of two numbers, namely 0 and 1. Okay, so 0 divided by 1 is equal to 0. And then negative 17, a negative number, can be written as negative 17 over 1. Okay, so again, the numerator and the denominator are all integers. Next, another way of writing a rational number is through fractions. Okay, so this is already in fraction form. So negative 2 is an integer and 3 is also an integer. So that is a quotient of negative 2 and 3. Another one, so we have 5 over 8 or the quotient of 5 and 8, which are both integers. Another one is a decimal. So decimals can be written as a quotient of two integers. So this is a terminating decimal and it can be expressed as 1/2. Later on, we will learn how to express numbers from decimals to fractions and vice versa. And we have here an example of a non-terminating but repeating decimal. Okay, and that can be expressed in fraction as negative 1 over 3. Okay, so those are some examples of rational numbers. Okay, so we have here irrational numbers on the other hand. So irrational numbers are those that do not belong in the set of rational numbers. So it says there, irrational numbers are the set of real numbers that cannot be expressed in the form of a fraction p over q, where p and q are integers. So the denominator q is not equal to 0. So same condition, but for irrational numbers, they are numbers which cannot be expressed using this form wherein p and q are integers. So here are some of the irrational numbers that we have. So the value of pi, okay, that is a symbol for pi, and that the value of pi is 3.14159265, and we have here an ellipsis. It means that it is a non-terminating decimal, so the value of pi is very long. Okay, so there are a lot of numbers that follows after that. It's non-terminating. Next, okay, so it is a non-repeating and non-terminating decimal. Okay, so we have decimals that are rational numbers, right? Just like the previous examples. So we include repeating decimals, repeating and non-terminating decimals as rational numbers, as well as terminating decimals. But if it is like this, it is non-repeating, at the same time it is non-terminating, then they are irrational numbers. Next is the value of square root of 2. So that is read as square root of 2. Let me write that. So in the next lesson, we are going to learn about square roots or roots. Square root, oh wait, square root only. Square root of 2. Okay, that is read as square root of 2. And if we are going to square that using our calculator, so the value is also a non-repeating, non-terminating decimal. Next is the value of E, or Euler's number, and it is also a non-repeating, non-terminating decimal. And of course, you have here the golden ratio. Okay, so it is very long, so we have here an ellipsis. We should remove the extra dots here. Okay, so let me remove that. Okay, so ellipses only comprise of What's this? 3 dots. Okay, let me erase that first. Okay. There you go. So here are the examples of irrational numbers. And let's move on with converting rational numbers from one form to another. So the first one is converting fractions to decimals. Let's go on with some examples. Okay, for number one, we need to convert 1/4 or 1/4 into its decimal form. Okay, again, we read that as 1/4 or 1/4. So the first step that we are going to do is, by the way, we have here two solutions. So for solution one, we simply divide the numerator by the denominator. Okay, so when we do that, we are going to use this method. So the numerator is always inside the division symbol. Okay, so we have here 1 inside the division symbol, and then we have the denominator outside. Okay, and since 1 is smaller than 4, so we are going to annex zeros. Okay, but before annexing zeros, we have to put a decimal point after the number and then add a 0. Okay, so we have 1.0, but we will first consider that as a whole number. So we are going to divide 10 divided by 4, and the result we are going to put it here. Okay, we will align it with 0. So 10 divided by 4 is what? 2. Okay, so if you have observed, we have included here a decimal point. Okay, we have already put the decimal point in line with this decimal point. Okay, now we follow the same rule or steps in dividing. So after we have divided that, we are going to multiply 2 and 4. So 2 times 4 is equal to 8. Okay, so we have aligned it one's digits to one's digit. So 10 minus 8 is equal to 2, and I think we can annex one more 0, so bring down 0, and we have 20 divided by 4, and 20 divided by 4 is equal to 5. And then we multiply it again. 5 times 4 is equal to 20. And subtracting the two numbers, 20 minus 20 is equal to 0. That means that 1/4 in decimal is 0.25. Okay, or simply 0.25, but it's better if we are going to put 0. Okay, 0 before the decimal point. Another solution is by multiplying the fraction by a number to make the denominator a power of 10. Okay, are you familiar with powers of 10? So the lowest power of 10 is 10 followed by 100 followed by 1000 and then 10,000 and so on. We have here, yes, those are the powers of 10. Okay, so let us write again our given. We have 1/4. And then can you think of a number which we could multiply with 4 to come up with either 10, 100, 1000? Can you think of a number? Of course, we cannot have 10. Okay, because when we multiply 4 by 2, the result is already 8. So let's try 100. Is there a number that we could multiply with 4 to get 100? That's right. We can multiply the denominator by 25. Okay, and when we multiply the denominator by a certain number, we are also going to multiply that to the numerator. Okay, so we will multiply 1 and 25 as well. After that, we simplify. So numerator times numerator. 1 times 25 is equal to 25, and 4 times 25 is equal to 100. Now we read that as 25 hundredths. Okay, and when we rewrite that as a fraction, so we write 25 and then count the number of zeros in the denominator. So we have 2. It means that we will move the decimal point 2 places to the left. So we have 1 and 2. Okay, there you go. Step by step. So 2 decimal places to the left, and we have 0.25, or simply 0.25. So it's up to you which solution would you prefer to use. Okay, but either both methods are acceptable. Another example. So example number 2, we need to express 2/5 as a decimal form. Okay, or 2 over 5. Now solution 1, we are going to divide 2 divided by 5 again, just like what we've done in example number 1. So 2 divided by 5 is written as this. Okay, again, the numerator or the dividend is inside our division symbol, and the divisor is outside. And again, since 2 is smaller than 5, so we are going to annex a 0, but we have to use or put a decimal point. Okay, now we can divide 20 divided by 5. 20 divided by 5 is equal to 4, and we will align it with 0. Okay, and we have here a decimal point, of course, in line with the decimal point here. Now we multiply 4 times 5, that is equal to 20, and 20 minus 20 is equal to 0. Okay, no need to add more zeros because we already have the answer, which is 0.4 or 0.4. For solution 2, we are going to find a number which we could multiply with 5 to get a power of 10. And I know by now you know what that number is. Okay, so the smallest number which we could get, or the smallest power of 10 that we could get, is 10, right? Because 10 is a multiple of 5. Now, what number have we multiplied with 5? Or could we multiply with 5 to get a 10? Alright, so we have 2. And then, since we are multiplying 2 to the denominator, we are also going to multiply 2 to the numerator. And 2 times 2 is equal to 4, and that's it. Just like what we've done earlier. So write the numerator and then count the number of zeros. So we only have 1 0. It means that we are going to move our decimal point to the left, 1 place to the left. Okay, so the decimal point of this number is here, and we are going to move to the left once. So our final answer is 0.4 or 0.4. So that is the answer for example number 2. Here's another example. So we have example number 3. This time we have a negative fraction. Okay, convert negative 1/3 into its decimal form. So solution 1, or we are going to use solution 1 because we cannot use solution 2 because there is no number which we could multiply by 3 to get a power of 10. So we will use the first method. Okay, so we have, we disregard first the negative sign and simply write 1 inside the division symbol, and of course our divisor, which is 3, outside. Again, we annex a 0, but we first put a decimal point to know where our decimal point is in our quotient. Now we have 10 divided by 3 is equal to 3, and then 3 times 3 is equal to 9. We subtract them, the result is 1. We again annex a 0 and get a 10. 10 divided by 3 is again 3. So it is a continuous process. And 3 here is repeating. So we can put this line or a bar on top of these two numbers and express negative 1 over 3 as negative 0.33. When we rewrite it, we make sure that we include the sign of the given. Okay, so this is a repeating decimal, so this is still considered a rational number. Example number 4. So we are going to convert 1 and 1 over 16 into its decimal form. But this time we are going to use solution 2. Okay, wherein we are going to find a number that will make the denominator a power of 10. And what do you think is that number? So we cannot have 10. 100 we cannot. And about 1000, let us check. Okay, so the lowest power of 10 that we could get, or a multiple of 16, that is a power of 10, is 10,000. And what could we multiply with 16 to get 10,000? Or 10,000 divided by 16, the result is 625. And we are going to multiply that as well with our numerator. Okay, so we are going to disregard 1 first and multiply only 1 and 16 by this fraction. So 16 times 625 is again 10,000, and we have 1 times 625 is equal to 625. And then to express that as a decimal, so we write 625 first and then count the number of zeros. So we have 1, 2, 3, 4. That means that our decimal point is here, and we are going to move 4 places to the left. So we have 1, 2, 3, and 4. Let me draw that. Okay, so we have 1, 2, 3, and 4. There is a space here, which means that we have to annex a 0. So we are going to add 1 0 because there is a space here. Okay, so the value of 1 over 16 is 0.0625, and let us not leave our whole number 1. So we have 1.0625. That is the equivalent of 1 and 1 over 16 in decimal. Next, we will do the reverse. So we are going to convert decimals to fractions this time. But first, we are going to deal with terminating decimals. When we say terminating decimals, so it is a decimal with no repeating numbers on it. Okay, to change rational numbers in decimal forms, express the decimal part of the numbers as a fractional part of a power of 10. Okay, so again, you are familiar with the powers of 10. We have 10, 100, 1,000, 10,000, 1 million, and so on. Here are some examples. We have here a negative decimal, negative 4.5, or we read that as negative 4 and 5 tenths. So upon reading it, we are already writing it or expressing it as a fraction. So negative 4 and 5 tenths, that is how we read it, because the place value of 5 here is in a tenths place. Okay, its place value is in tenths place. So that is read as -4 and 5/10. We could still simplify this by reducing 5 and 5/10. We could divide them, or we could cancel them and divide them both by 5. So 5 divided by 5 is equal to 1, and then 10 divided by 5 is equal to 2. So the simplified form of this is -4 and 1/2. Example number 2, so we have 2.713. Okay, so how do you read that? Instead of saying 2.713, so we are going to say 2 and 713 thousandths. Am I right? Yes, because the place value of the third digit is in thousands place. So that is read again as 2 and 713 thousand. So the denominator is 1000. And since we cannot simplify 713 over 1000 any longer, so that is our final answer. Next, this time, how about if we are going to convert decimals to fractions? But we have non-terminating but repeating decimals. Though it is not terminating, but it is repeating. Okay, so the first step is for us to identify the repeating digits. Step 2, count the number of repeating digits. And then number 3, write the numerator and the denominator using the rule below. So the numerator is the repeating digit or digits. If there is only one repeating digit, so that is the numerator. And then the denominator is the number of nines based on the number of repeating digits. Okay, to have a clearer view of that, we have an example. So example number 1, we are going to change 0.2 into fraction. So 2 here has a bar on top of it. It means that 2 is our repeating decimal. Okay, so step 1, we are going to identify the repeating digit or digits, but there is only one repeating digit here, and that is 2. Step 2, count the number of repeating digits, and that is only 1. There we only have one repeating digit. And then we follow this rule for step 3. So our numerator is the repeating digit, which is 2. And then our denominator is the number of repeating digits, but we will put 9. Okay, we will only put 1 9 in the denominator since there is only one repeating digit. That means that 0.2222 or 0.2 with a bar on top can be expressed as 2 over 9. Example number 2. So again, we are going to change -1.35 to its fraction form. Again, for step 1, we identify the repeating digits. So we have two repeating digits here, which are 3 and 5, or simply 35. And then there are two repeating digits here. So that means that we will have two nines as a denominator. So we express -35 with a bar on top as 35 over 99. And we include our whole number here, -1. So we have -1.35, 3535, and so on, as -1 and 35 over 99 as its a fractional form. Okay, so when we write our final answer, we don't forget to include the whole numbers as well as the sign of the given. Okay, here is another example. So we have 7.215 as a fraction. So the repeating digits here are 2, 1, and 5, or 215. And since there are 3 repeating digits, so we are going to include 3 nines in the denominator. Okay, so to express this part of the fraction as this part of the decimal as a fraction, so we write it as 215 over 999. But our final answer should include the whole number 7. So the equivalent of 7.215 repeated is equal to 7 and 215 over 999. That is our final answer for example number 3. Another, so we have this, but this time we have a digit that is not covered by the bar. It means that only 11 here is the repeating decimal or the repeating numbers. So how are we going to solve or write that in fraction? So we also have here steps that we can follow. For step 1, we identify the non-repeating digits. Okay, and which is the non-repeating digit in our decimal? It is 2. Okay, we have 2 here as the non-repeating digit. And the number 2, count the number of non-repeating digits. So there is only one non-repeating digit here, which is the 2. Number 3, count the number of repeating digits. So there are 2 repeating digits because we have 2 ones. And then number 4, subtract the non-repeating digits from the decimal part. So that will be our numerator. So our decimal part is 211. We are going to subtract our non-repeating digit, which is 2. Okay, so that is how it will look like. 211 minus 2, that is 209. That will be our numerator. Next, the denominator is composed of nines followed by zeros. So this time it is not only nines, but we will include zeros. Okay, so it is determined by the number of repeating and non-repeating digits. So the number of nines is based on the number of repeating digits. Take note of that. The number of 9 is number of repeating digits, and the number of zeros are based on the number of non-repeating digits. Okay, so we will start with writing the number of repeating digits before the number of repeating or non-repeating digits. Okay, so we have 0.211 is equal to 209. We have already obtained this from step 4. And then we have 2 repeating digits, right? So we have to include 2 nines in the denominator, and then we have 1 repeating digit, so we are going to put 1 0 in the denominator. So when we combine those two, we will obtain 990. So that is the equivalent of 0.211 or negative 0.211, wherein 11 is the repeating decimals. Were you able to get that? Let's have another example. For example number 5, we are going to express 2.3215 as a fraction, wherein 15 here is the repeating decimals. So again, for step 1, we identify the non-repeating digits, which are 3 and 2. So we have 32. Number 2, count the number of non-repeating. There are 2 of them. Okay, so that will determine the number of zeros, right? So we'll have 2 zeros later on in our final answer or in our denominator. Count the number of repeating digits. So the number of repeating digits are also 2. We have 1 and 5. So it means that we will have 2 nines in our denominator. Number 4, subtract the non-repeating digits from the decimal part. So this will be the numerator. Okay, so our decimal part is 3215. We will subtract 32 and we will obtain the difference, which is 3183. This again is our numerator. And then the denominator is composed of the number of nines, number of repeating, and number of non-repeating. Okay, so the denominator is 9900 because we have two repeating and two non-repeating decimals. Okay, so here is our final answer. The equivalent of this decimal is 2 and 3183 over 9900. Next example. So we have here a negative decimal. Alright, so we follow the steps in solving or in converting non-terminating but repeating decimals to fractions. For step 1, again, we identify our non-repeating digits, which are 8 and 1. Okay, so we have 8 and 1 as our non-repeating digits. Number 2, we count the number of non-repeating digits. So how many? We have 2. It means that we will have 2 zeros in our denominator. Let me just put that, 2 zeros. And then number 3, count the number of repeating digits. We have 1, 2, and 3. Okay, so there are 3 repeating digits. It means that we will have 3 nines in our denominator. So 9, 9, and 9. Next, number 4, subtract the non-repeating digits from the decimal part. So our non-repeating digits is 8 and 1 or 81. And then our whole decimal is 81,547. And when we subtract this two, the result is 81,466. Okay, so we have 81,466. That will be our numerator. And then, there you go. And then we annex or we put the number of non-terminating and the number of non-terminating, or the number of repeating and the number of non-repeating digits. So we have 3 nines and 2 zeros. There you go. So the equivalent of this fraction is negative 3, or the equivalent of this decimal is negative 3 and 81,466 over 99,900. Now let us check your understanding of our lesson as we answer the following problems. Okay, for the first one, we are going to convert the following fractions to decimals. Okay, we are going to convert the following fractions to decimals. Can you still recall how to convert fractions to decimals? Okay, we have two methods, right? So it's either we divide the numerator by the denominator, or if we could identify a number which we could multiply by the denominator to get a power of 10, we could do that. Okay, so for number 1, we have 2 over 5. Okay, so let us use method 2, wherein we will identify a power of a number which we could multiply by 5 to get a power of 10. And what number is that? That is 2, for us to get the lowest power of 10, which is 10. And then since we are multiplying by 2, we will also multiply 2 with the numerator. So 2 times 2 is equal to 4. Okay, so 4 over 10, that is 4. And again, we will move, if the decimal point is here, we will move the one place to the left because we have 1 0 here. Okay, so 0.4, or we can write that as 0.4. That is the answer here. Example number 2, or problem number 2, we have 1 and 4 over 25. Again, we can identify a number, or we can make 25 a power of 10 by multiplying 4 to get the power of 10, which is 100. So we will also multiply 4 in the numerator. So we have 4 times 4 is equal to 16. We do not forget our whole number 1. So we have 1 and 16 over 100. And 16 over 100 can be written as 0.16. And then we include our whole number, which is 1. So the equivalent of 1 and 4 over 25 is 1.16. Number 3, so we have here negative 3 and 17 over 20. We could multiply 5 to the denominator to get 100. And we will also multiply that by our, or with our numerator. So 17 times 5 is equal to 85. Don't forget negative 3, so we have negative 3 there. And then we have 85 hundredths, or in decimal, that is 0.85. And then negative 3, our whole number. So the final answer here is negative 3.85. Number 4, so we have 3 over 8. We can multiply a number. I think it is 10,000. So we could multiply it by a number to get 1,000. And what is that number? It is 1,250. I mean, we could multiply a number by 8 to get 10,000. Okay, the result here is 10,000. So we will also multiply 1,250 by 3, and the result is 5,750. Okay, 5,750. I think we could remove 0 here. So instead of multiplying 1,250, we could multiply 125. Okay, to remove the extra 0. Okay, so that is 575 over 1,000, or simply 0.575. We put 0 because we don't have a whole number, so we have 0.575. Number 5, we have negative 7 over 2. So again, we have 2. We can make it a power of 10 by multiplying 5. So 2 times 5 is equal to 10. We will also multiply 5 by the numerator. So 7 times 5 is 35. Don't forget the negative sign. And then we write it as whole number first, since there is only 1 0 and our decimal point is here, so we will move only one place to the left. So we have 3.5 or negative 3.5 because we have a negative sign in the given. The final answer here then is negative 3.5. Next, so this time we are going to convert decimals to fractions. So as you can see, for number 1 to 5, the given are all terminating decimals, so we have no problem here. Okay, so for number 1, we can write that as negative 2 and then 5 over 10. But we can still simplify it. 5 and 10 are both divisible by 5. So we divide them both by 5. So 5 divided by 5 is 1. 10 divided by 5 is 2. So the final answer is negative 2 and 1/2. Number 2, we have 7.13. So we have the whole number first, 7. So we have 7 and 13 over 100. We can no longer simplify this, so that is the final answer. Next, we have 0.0078. The place value of 8 here is 10,000. It means that we can write this as 78 over 10,000. But we can still reduce it by dividing 78 and 10,000 by 2. So 2 or 78 divided by 2 is equal to 39, and 10,000 divided by 2 is equal to 5,000. So we will write that as 39 over 5,000. Next, we have 9.03, or 9 and 3/10 or 300ths. So that is the fraction form of 9.03. And for the fifth one, we have negative 11 and 1600ths, since the place value of 6 is 100. And then we can still divide this by 4. So 16 divided by 4 is 4, and 100 divided by 4 is 25. So the final answer is negative 11 and 4 over 25. So number 1, so we have negative 2 and then 45 over 99, since we have 2 repeating decimals. Number 2, we have 261 over 999, because there are 3 repeating decimals. Number 3, we have 21 and 789 over 999. Number 4, so we have negative 8, and then 1, 2, 3, 4 is our decimal minus the non-repeating decimals or digits, which is 12, over the number of number of repeating decimals, which is 2. So we have 2 nines and then 2 zeros, because there are also 2 non-repeating decimals. Simplifying, so we have negative 8 and 1226 over 9900. Next, number 15. So we have 16 and then 1, 2, 3, 2, 1 minus 1, 2, 3. There are 2 repeating decimals or repeating digits, so we have 9, and then 3 non-repeating digits, so we have 3 zeros. So we subtract 1, 2, 3, 2, 1 minus 1, 2, 3. So that is 11 minus 3, we have 8. This will be 1. We borrow from 3, so we have 11. This will be 2. 11 minus 2 is 9. 2 minus 1 is 2. And then we have 2. So the final answer is 16 and 12,298 over 99,000. Hello dear students, today we are going to learn about the operations on rational numbers, and we have learned last time that rational numbers are numbers which could be written as the quotient of two integers. So today we will learn how to add, subtract, multiply, and divide decimals as well as fractions. This is teacher Mary Jane, and I hope that you learn from our discussion. All right, so we have here examples on how to add and subtract similar fractions. Okay, what does it mean when we say similar fractions? So these are fractions which have the same denominators. All right, so we have here a rule. To add or subtract similar fractions, we simply add or subtract the numerators, write the sum or difference over the common denominator. And of course, we reduce the answer to lowest term if needed. Okay, so what we have to consider in adding similar fractions, adding or subtracting similar fractions, is the numerator. And then we just copy the denominator. Okay, let's have examples. So example A, we are going to add 3/5 and 1/5. So if we are going to add that, so we write it first in horizontal form, or you can write it using vertical. You can write them vertically. Okay, it's up to you, whichever is uh, more comfortable or easier for you. Okay, now as we have said in the rule above, we simply add or subtract the numerators. So we have 3 plus 1, that is 4. And then our common denominator is 5. So the sum of 3/5 and 1/5 is 4/5. Okay, that is the answer. Now how about for subtraction? So we are going to subtract 4/10 minus 2/10. So again, we write it in any way that we want. So for the solution, we are going to write them horizontally. So we have 4/10 minus 2/10, and then we copy first our common denominator, which is 10, and then subtract our numerators, since subtraction is our operation here. So 4 minus 2 is equal to 2, and we can still simplify these numbers. We can divide 2 and 10 by 2, yes. So 2 divided by 2, we cancel, and we have 1. And the next 10 divided by 2 is equal to 5, so we cancel 10 here and write 5 below or beside it. Now we are right, so we have 1/5 or 1/5. That is the difference between 4/10 and 2/10. Next, so this time we are going to look at problems involving mixed numbers with similar fractional parts. Okay, so mixed numbers means that we have a whole number included. Add or subtract the numerators and write the sum or difference over the common denominator. And of course, we reduce the answer to lowest term if needed. But what will we do with the whole numbers? We simply add or subtract them as well. Let's have an example. So we have your example A. Add 4 and 1, 9, and 5 and 2, 9. So we write them horizontally, and we have already added here the whole numbers. So 4 plus 5 is equal to 9. That's why we have here 9. And then the common denominator is 9. So we write there the denominator 9. And of course, we add our numerators. So we have 1 plus 2 is equal to 3. But 3 and 9 have a common factor, which is 3. So we can divide 3 and 9 by 3. to simplify this fraction. So 3 divided by 3 is equal to 1, and 9 divided by 3 is equal to 3. We rewrite it. Our final answer is 9 and 1/3. Example B. So we are going to subtract this time. Subtract 23 and 7 over 28 minus 2 and 2 minus 2 and 2 over 28. Okay, so we write them horizontally again, and there is the difference between 23 and 2 for our whole numbers. So 23 minus 2 is equal to 21, so that is our whole number. And then copy our common denominator, which is 28. Okay, and 7 minus 2 here is equal to 5. And 5 and 28 do not have any common factor. That's why our final answer is 21 and 5 over 28. Next, so to add or to subtract a fraction or a mixed number from a whole number. Okay, so this time we have a whole number as the minuend or the addend. Rename the whole number as a mixed number whose denominator is the same as that of the fraction. Then subtract in the same way you subtract fractions or mixed numbers. We reduce the answer to lowest term if needed. Okay. So if we have a whole number, we simply write it as a fraction, but its denominator will be the same with that of the denominator of the fraction that we are adding or subtracting. Here is an example. So we have here a whole number 5. We are going to subtract 2/3. And what are we going to do? We can express 5 as 15 over 3. Okay, because 15 divided by 3 is equal to 5. Or we simply multiply our, what is this? Our denominator, the denominator of the fraction, to that of our whole number. Okay, so 3 times 5 is 15. And of course, divide it again by the denominator for us to get 5. Okay, now we can already apply what we have learned earlier. So simply copy the common denominator, which is 3, and then subtract the numerators. So 15 minus 2 is equal to 13. We can also express 13 over 3 as a mixed number. So how did we get 4 and 1/3? So let me show you how we've done that. Okay, so in the simplifying fraction or mixed fraction, we divide the numerator by the denominator, and then we divide. So 13 divided by 3 is equal to 4, and then 4 times 3 is equal to 12, and then the difference between 13 and 12 is 1. That is actually the remainder, but we express the remainder and our divisor as a fraction. Okay, so we copy our whole number 4 and then put the remainder in the numerator, and then the denominator is the divisor, which is 3. That's why the answer here is 4 and 1/3. Example B, subtract 9 minus 3 and 3/16. Again, we can express 9 as 8 and 16 over 16. So actually, we can also write 9 times 16 is, what is the product of 9 and 16? 16 times 9. So 9 times 6 is 54. 9 times 1 is 9 plus 5. So it can be 144 over 16. Okay, but since we have here a whole number, it is easier for us to simply write it this way. Okay, so we have 9 here. We just remove 1. Okay, and that 1 is equal to 16 over 16, since 16 divided by 16 is equal to 1. And then we are left with 8. Okay, so if you simplify 8 and 16 over 16, that is still equal to 9. Okay, to make it easier for us to subtract, we have made it 16 over 16 because our subtrahend is the its denominator is 16. Okay, for them to be similar fractions, and we write it horizontally. So we already have there the difference, which is 5. 8 minus 3 is equal to 5, and then our common denominator is 16, so that will be the denominator, and then 16 minus 3 is 13 over 16. And since we cannot simplify further, so that is the final answer, 5 and 13 over 16. Right, this time we are going to deal with dissimilar fractions and mixed numbers. So we are going to add and subtract them. Okay, we have here our rule. It says there to add or subtract dissimilar fractions, we change them to similar fractions by finding their least common denominator. I hope you are still familiar with the least common denominator. Add or subtract the numerators and write the sum or difference over the common denominator. And we reduce them if needed. Okay, so we have here the similar fractions 1/3 and 2/4. We are going to add them. Okay, so unlike what we've done a while ago, we cannot just add 1 plus 2 and then 3 plus 4. That is wrong. We have to make them similar fractions by finding the LCD. Okay, so for us to get the LCD, we list down the multiples of our denominators. So we have here the list of the multiples of 3 and list of the multiples of 4. And then the common number here is 12. That's why the LCD here is 12, least common denominator. After that, we will write the fractions as similar fractions. So we write 1/3 as a fraction wherein its denominator is 12. Okay, so how do we do that? We multiply 3 by a certain number to get 12, and that number is 4. Okay, and just like what we've done before, when you multiply by the denominator, we also have to multiply it to the numerator. So we have 1 times 4 is equal to 4. So the equivalent of 1/3 is 4 over 12. And then 2/4 on the other hand, so we have there 12 again as the denominator, and we multiply it by 3 to obtain 12. Of course, when we multiply 3 to the denominator, we have to multiply it with the numerator. So we have 2 times 3 is equal to 6. So the equivalent of 2/4 when we change the denominator into 12 is 6 over 12. Now they are already similar fractions, so we can add them. Okay, so 4 plus 6 is 10, and then copy the common denominator, which is 12. Now we can still simplify 10 and 12 because they are both divisible by 2. So 10 divided by 2 is equal to 5, and then 12 divided by 2 is equal to 6. So the simplified form, or the simplified form of the answer is 5 over 6. That is our final answer to this example. Another example, so we are going to subtract 3/6 and 1/5. Again, we find the LCD, so you don't have to do this actually if you are already familiar with the LCD. So we just identify the LCD, which is 30, and then we change them as equivalent into its equivalent fraction. Okay, so 6 times what number to get 30? That is 5. Okay, so we have multiplied 6 by 5 to get 30. So we are also going to multiply 3 by 5. So 3 times 5 is equal to 15 over 30. That is the equivalent of 3/6. And then we have 1/5. So again, its denominator will become 30 when we multiply 6. So times 6 also to the numerator. 1 times 6 is equal to 6. Now that they are already similar, we can apply our operation, which is subtraction. So we have 15 over 30 minus 6 over 30. So 15 minus 6 is equal to 9, and then copy our common denominator, which is 30. And of course, 9 and 30 have a common factor, which is 3. So we can divide them both by 3. 9 divided by 3 is equal to 3, and 30 divided by 3 is equal to 10. So this is equal to 3 over 10, or 3/10. Okay, that is the final answer to this example. Next example. This time we have a mixed number. Okay, so we have 2 and 3/5 plus 1 and 2/8. So we disregard first our whole numbers and get the LCD of our denominators 5 and 8. So 5 and 8 are actually both have the same multiple, which is 40. The least common multiple of the two is 40, so that is their LCD. And then we rewrite our fractions 3/5 and 2/8 as fractions bearing the denominator 40. Okay, the pair of 5 here is 8, so we also multiply 8 to the numerator to get 24. And then the same with 2/8. So to make it 40, we have to multiply by 5. The same with the numerator. So 2 times 5 is equal to 10. Now we can add the numbers. So we have 2 and 24 over 40 plus 1 and 10 over 40. Don't forget to add again our whole numbers once you are done writing the equivalent of the fractions. So we already have the sum of the whole numbers. 2 plus 1 is equal to 3. And then we have 24. 24 plus 10 is equal to 34. And then our common denominator is 40. But this 2 can still be divided by 2. So we cancel. 34 divided by 2 is equal to 17. And 40 divided by 2 is equal to 20. That makes our final answer as 3 and 17 over 20. Here is another example for subtracting mixed numbers. Okay, so the LCD of 4 and 6 is 12 because that's the least common multiple of these two numbers. After that, we rewrite them as similar fractions. So 1/4, to make the denominator 12, we multiply by 3. So we multiply 3 also to the numerator. So 1 times 3 is equal to 3. And then our next fraction is 1 over 6. And to make the denominator 12, we multiply by 2. So 6 times 2 is equal to 12. And the same for the numerator. 1 times 2 is 2 over 12. So those are their similar, they are already similar fractions. We can include our whole numbers now and subtract them. So 3 minus 2 is equal to 1. And then 3, wait, it's just the same, so let me use this. 3 minus 2 first, the whole numbers. 3 minus 2 is equal to 1. And then our the numerators, we subtract them. So 3 minus 2 is equal to 1. And then copy our common denominator, which is 12. We can no longer simplify this. So that is the final answer to example D. Next, we will continue with multiplication of fractions. So how do we multiply fractions? It says there, to multiply fractions, we multiply the numerator to get the numerator, or we multiply the numerators to get the numerator of the product. Multiply the denominators to get the denominator of the product. Then simplify the product if needed. We have here an example. So we multiply 2/3 and 1/2. Okay, so we can write them horizontally. And as it says here, we multiply numerator by numerator. So 2 times 1 is equal to 2. And then 3 times 2 is equal to 6. And then we simplify them because they are both divisible by 2. So 2 divided by 2 is equal to 1. And then 6 divided by 2 is equal to 3. So the final answer here is 1/3. Example B, we have 2/3 and 1/5. We have to find its product. So we write them again in this manner. So 2 times 1 is equal to 2. 3 times 5 is equal to 15. We can no longer simplify them. So that is the final answer. Alright, so let's try to solve more examples. So we have example B. We have to multiply 2/3 and 1/4. So I will introduce to you another method of multiplying fractions, which is called the cancellation method. So in this method, we are going to cancel pairs of numerators and denominators that have common factors. Again, we will cancel numerators and denominators. We cannot pair up numerator to numerator or denominator to denominator. So we have here an example. So we have 2/3 times 1/4, and as you can see, 2 and 4 have a common factor, which is wait. Okay, 2 and 4 have a common factor, which is 2. That's why we will cancel these 2 and divide them both by 2. So if the result, when we divide 2 divided by 2, so the result is 1, and then 4 divided by 2 is equal to 2. Apart from those, there are no other pairs that we could cancel, so we multiply numerator by numerator and then denominator by denominator. So 1 times 1 is equal to 1, and 3 times 2 is equal to 6. That is the answer to example C. Next, we have example B. Multiply 3/4 and 8/9. Again, let us check if there are there is a numerator and a denominator that have common factors. So in this case, 3 and 9 have common factors, which is 3. So we divide them both by 3, and the result for this numerator, 3 divided by 3 is equal to 1. That's why we have 1 here. And then 9 divided by 3 is equal to 3. We could also divide 4 and 8 because they are both divisible by 4. So when we do that, 8 divided by 4 is equal to 2, and 4 divided by 4 is equal to 1. And there are no more common factors between the numerators and the denominators. So we are going to multiply this fraction. So we have 1 times 2 is equal to 2, and 1 times 3 is equal to 3. That means that the product of 3/4 and 8/9 is 2/3. It is already in its simplest form. So you can still use our previous method, but for you to easily, okay, so that you don't have to simplify and simplify, you'd better use cancellation method. Another rule, okay, same rule, but we will have another example. So in this case, our whole number is our divisor is a whole number. Okay, so we write it as well as a fraction. So we will have 2/3 divided by 6/1. After that, we change our operation into multiplication. Okay, right. So we change our operation into multiplication and then multiply it by the reciprocal of 6/1, which is 1/6. So for this, we can cancel 2 and 6 because they are both divisible by 2. And 2 divided by 2 is equal to 1. 6 divided by 2 is equal to 3. And we can now multiply. So 1 times 1 is equal to 1. And 3 times 3 is equal to 9. So the final answer here is 1/9. Next example. So for this example, we have this rule. To divide mixed numbers, rewrite them as improper fractions. Find the reciprocal of the divisor and change the operation to multiplication. And again, we use cancellation whenever possible. So here is the example. We are going to divide 7 and 1/2 by 1 and 1/2. So says there in the rule, we change the mixed number into improper fraction. Okay, so we have obtained 15/2 here by multiplying 2 and 7. So 2 times 7 is equal to 14 plus 1. So we have 15 and then copy the denominator 2. Next, 2 times 1 is equal to 1 plus 1. So we have 3/2. Next step, we change the operation into multiplication and write the reciprocal of the what is this? The divisor. Okay, so we we will obtain 15/2 times 2/3 after doing that. The reciprocal of 3/2 is 2/3. Okay, and then we can cancel numerators and denominators with common factors. So 15 and 3 have a common factor which is 3. So 15 divided by 3 is equal to 5 and 3 divided by 3 is equal to 1. We can also cancel 2 and 2 as they are both divisible by 2. So that will be equal to 1. And then we can now multiply. So 5 times 1 is equal to 5. 1 times 1 is equal to 1. Again, since the denominator is 1, so we write it as a whole number. Okay, so the final answer here is 5. Now we have here a trial problem. Multiply 1/5 by, or divide 1/5 by 3 and 7/10. I will give you a few seconds to try and answer this problem. And then later on we will solve it together. Okay, let's check. So we have 1/5 divided by 3 and 7/10. We have here a mixed number, so we change it first into improper fraction. We have 10 times 3 is 30 plus 7, so 37/10. And then we copy our operation as well as our dividend. After that, we change this into multiplication. We copy our dividend first and then get the reciprocal of our divisor. So we will have 10 over 37. Now, do we have common factors? Yes, we have 5 and 10. Their common factor is 5. So 5 divided by 5 is 1. 10 divided by 5 is 2. We can no longer cancel any pairs, so we multiply 1 times 2 is equal to 2, and 1 times 37 is equal to 37. That is the final answer to this problem. Did you get it? Very good if you did. This time we are going to deal with operations on decimals. We have here steps on how to add or subtract decimals. So step 1, we write the decimals in columns and make sure to align the decimal points of the addends. Okay, let's have an example right away. So we have add 0.456 or 456 hundredths, thousandths I should say, 456 thousandths, 5 tenths, and 9,812 ten thousandths. So we are going to add them all. For step 1, we have to align them in columns. So all of the decimal points should be aligned. So that is the result. After that, step 2, make the number of decimal places equal by annexing zeros to the decimal numbers. Okay, so for us not to be confused, we can annex zeros. Okay, so we can add a 0 here as well as zeros in this part. So that again we will not be confused. Okay, after that, let's proceed to step 3. Add or subtract the numbers from right to left in the same way you add whole numbers. Regroup if needed. Align the decimal points of the sum with the decimal point of the addends. Okay, so we start from the right. So we have 0 plus 0 plus 2 is equal to 2. 6 plus 0 plus 1 is equal to 7. 5 plus 8 is equal to 13. So carry 1. 1 plus 4 plus 5 plus 9 is equal to 19. So carry 1. And then we have 1 plus 0 plus 0 plus 0 is equal to 1. And then we align the decimal point of our sum by the decimal point of the 3 addends. Alright, so that is our final answer, or this is the sum of those 3 decimals. Next, we have to add 241 thousandths plus 1,221 ten thousandths and 5. As you can see, 5 here is a whole number. Okay, so let us first align the 2, and then for 5, since it is a whole number, so its decimal point is actually here, okay, after the number. Okay, so we will now annex zeros, step 2, for us not to be confused. Alright, so that is the result. After that, we can add from right to left. So we have 1, and then 1 plus 2 is equal to 3, 4 plus 2 is equal to 6, 2 plus 1 is equal to 3, and then 0 plus 0 plus 5 is equal to 5. The decimal point will be here. So the final answer is 5.3631, or we read that as 5 and 3,631 ten thousandths. Next, this time we will have subtraction. Subtract 1.9372 from 4.025, or we read it as subtract 1 and 9,372 ten thousandths from 4 and 25 thousandths. Remember, it says there subtract from. It means that our minuend here is 4 and 25 thousandths, and our subtrahend is 1 and 9,372 ten thousandths. So this is how our solution will look like. Again, we annex 0, And then we can now subtract. So 0 minus 2 cannot be, we will borrow from 5. So 5 will become 4, and 0 here will become 10. We can now subtract 10 minus 10 minus 2 is equal to 8. And then 4 here cannot subtract 7, so we will borrow from 2. So 2 will be 1, and 4 here will become 14. Now 14 minus 7 is equal to 7. Now we have to subtract 1 minus 3, but again we cannot because 1 is lower, so we will borrow from the next digit or from the digit to its left. But we have 0 here, so we will move and borrow from 4. Okay, so 4 will become 3, and then 0 will become 9 because supposedly it should be 10, but we will borrow, or 2 will borrow, and 1 will borrow, and it will become 11. Now we can subtract. 11 minus 3 is equal to 8. 9 minus 9 is equal to 0. And 3 minus 1 is equal to 2. And then our decimal point is here, aligned with the decimal point of the two numbers that we are subtracting. And here is our final answer, 2 and 878 10,000ths. Example D. So subtract 4 minus 2.75. Our minuend is 4. Subtrahend is 2.75. Again, 4 here is a whole number. That means that the decimal point is after the digit. We annex zeros for it to be easier for us to subtract. We cannot subtract 0 minus 5, so we will borrow from the next digit, but it is also 0, so we will borrow from 4. 4 will become 3, and then 0 here will become 9, and the 0 at the last place will be 10. Now we can subtract. 10 minus 5 is equal to 5, 9 minus 7 is equal to 2, and 3 minus 2 is equal to 1. The decimal point is here. Our final answer is 1 and 25 hundredths. So that is for addition and subtraction. This time we will move on to multiplication of decimals. To multiply decimals, multiply them as you would multiply whole numbers. So you should be familiar with multiplication. Count the number of decimal places in both factors. The total number of decimal places in the factors should be equal to the number of decimal places in the product. Okay, let us look at this example. Multiply 375,000 times 346. So we align them vertically. So no need to align the decimal points because we are going to count the number of decimal places later on in our final answer. Okay, so we multiply like we are multiplying whole numbers. So 6 times 5 first is equal to 30. So 0 and then carry 3. 6 times 7 is 42 plus 3, so that is 45. 6 times 3 is 18 plus 4, so we have 22. 6 times 0 is 0 plus 2, so we have 2. Next, 4 times 5 is equal to 20. 4 times 7 is equal to 28 plus 2, so we have 30. 4 times 3 is equal to 12 plus 3, so we have 15. And 4 times 0 is equal to 0 plus 1, so we have 1. Last, 3 times 5 is equal to 15, carry 1. 3 times 7 is equal to 21 plus 1, so 22. That should be 2. Wait. Let us change. Okay, let me check that again. So 3 times 5 is equal to 15. Am I right? 3 times 5 is equal to 15, and then 3 times 7 is equal to 21 plus 1, so it should be 22. Yeah, that's right. So instead of 1, this should be 2. And then 3 times 3 is equal to 9 plus 2, so we have 11. it should be 11. It should be 1. And then 3 times 0 is equal to 3 times 0 is equal to 0 plus 1. So we have 1. Okay. So we have 1, 1, 2, 5. We can now add the numbers. So we have 0, 5 plus 0 is 5, 2 plus 5 is 7, 2 plus 5 plus 2 is 9, 1 plus 1 is 2, and 1, bring down 1. Now we count the number of decimal places. So for this factor, we have 3. And for this factor, it is a whole number, so we will only consider the 3 decimal places. So there you go. There are 3 decimal places, so it means that we will move, if the decimal place is here, we will move 3 places to the left. Okay, so the final answer is 129.750. Next example, we have 300 times 200. So we have 0.03 times 0.02. Again, we multiply them as if they are whole numbers. 2 times 3 is 6. And then that will all be 0. It will also be 0. So you can actually stop here. And no need to put this part. But for our example, I have just placed it there. Okay. So when we add all of those, that is the result, and then count the number of decimal places. There are 2 decimal places here, plus 2 decimal places here. That's why we have a total of 4. So starting from here, we will count 4 decimal places. So 1, 2, 3, 4. The decimal point should be here. Okay, so here is our final answer. The product of 300s and 200s is 6 10,000s. This time we are going to divide decimals. Here are the steps that we need to follow. To divide decimals, multiply the divisor by a power of 10 or move the decimal point to the right to make the decimal number a whole number. Multiply the dividend by the same power of 10 or move the decimal point to the right as many places as move the decimal point of the divisor. And then, next, divide the decimals as you would divide whole numbers. Annex zeros to the right of the decimal point of the dividend until the quotient terminates or the digits in the quotient repeats. Place the decimal point in the quotient directly above the decimal point of the dividend. So those are the steps that we need to follow for us to solve or find the answer to our examples. Example A, we will divide 84 by 1.2. So we are going to place it in the division symbol. So 84 is inside since it is the dividend, and 1.2 is outside the divisor. And then we can we must make our divisor a whole number first. So how do we do that? We move our decimal place to the right. Okay, since we are moving it one place to the right, we will also do that with our dividend. Okay, and since there is no digit here in the last part, so we have to annex a 0. Okay, now we are dividing 840 by 12. Can now divide. So 8 divided by 12 cannot be, so we will take 2 digits. 84 divided by 12 is 7, and 7 times 12 is equal to 84. Subtract 84 minus 84, the result is 0. Don't forget that we still have another 0, so bring it down. 0 divided by 12 is equal to 0. And 0 times 12 is equal to 0 again. And subtract them, the result is 0. It means that the quotient of 84 and 1.2 is 70. Example B, we are going to divide 269 and 75 hundredths by 5. So again, we write it here like this, and then we can divide because there is no problem with our divisor. It is already a whole number. So 2 cannot be divided by 5, so we will take 2 digits. 26 divided by 5 is 5. 5 times 5 is 25. Subtract them, so we have 1. Bring down 9. Next, 19 divided by 5 is equal to 3. 3 times 5 is equal to 15. And when we subtract them, the result is 4. Bring down 7. 47 divided by 5 is 9. 9 times 5 is equal to 45. And then subtract. So 47 minus 45 is 2. And then bring down 5. So we have 25 divided by 5. The result is 5. 5 times 5 is equal to 25. And 25 minus 25 is 0. Now for our decimal point, we just have to align it here with the decimal point of our dividend. So 53.95 is all right. For the next part of our discussion, so let us look into some worded problems involving the operations on rational numbers. For our solutions, you can use this method or you can use this acronym. So we are going to use AGONSA. Okay, so A for what is asked, G for the given, O for the operation, N for number sentence, S for the solution, and A for final answer. By using this acronym, you can fully answer what is necessary in the problem solving given or in the worded problem given. Okay, so for problem number 1, we have here the freshman convention was held at the activity center with 12,567 seats. If 120 seats were not occupied, how many were occupied? So let's have A for what is asked. So the question there is how many seats were occupied? And then the given is the total number of seats is 12,567 and the number of unoccupied seats is 120. Now our operation is subtraction since we have to subtract for us to get our answer. Okay, subtract the number of seats with that of the unoccupied seats. And then for number sentence, of course, we write it as 12,567 minus 120. And subtracting the two, so 12,567 minus 120, so 7 minus 0 is 7. 6 minus 2 is 4. 5 minus 1 is 4. And bring down 2 as well as 1. So the final answer here is 12,447. And we say for the final answer, 12,447 seats were occupied in the convention center. Problem number 2. Problem number 3 says there, how many pieces of ribbon can you cut from 10 meters if each piece is 4 centimeters long? Okay, so what is asked first? How many pieces of ribbon can you cut from 10 meters if each piece is 4 centimeters long? For the given, so the total length is 10 meters and the length of each piece of ribbon is 4 centimeters. As you can see here, we have different units. So we have meters and centimeters. So we can convert centimeters to meters right away. So 4 centimeters is equivalent to 4 over 100 meters, or in decimal, we can write that as 0.04 meters. And for operation, of course, we are going to use division. Number sentence, 10 divided by 4 over 10, or we can write 10 divided by 0.04. And then for the solution, we have 10 divided by 4 over 10, but since it is division, we have to change the operation into multiplication and find the reciprocal of 4 over 100, which is 100 over 4. We can then cancel 100 and 4 because they are both divisible by 4. 100 divided by 4 is equal to 25. 4 divided by 4 is equal to 1. On the other hand, 10 here has a denominator of 1. So we can now multiply. 10 times 25 is 250, and 1 times 1 is equal to 1. So we don't have to write that. Our final answer is 20. So for the final answer, we can say that you can cut 250 pieces of ribbon from 10 meters, or from a cloth or any material that is 10 meters long. Problem number 4. Peter bought 3/4 kilograms of corn beets. He repacked this into 1/8 kilogram each. How many packs of corn beets was he able to make? Okay, so what is asked in the problem is that how many packs of corn beets can Peter make? For the given, the total weight is 3/4 kilogram, and the weight per pack is 1/8. Of course, our operation here is division because we are going to divide the corn bits into different packs, different weights, different packs with 1/8 kilograms as its weight. And then number sentence, so we have 3/4 divided by 1/8. And for the solution, again, this is division, so we are going to change the operation into multiplication and then multiply our dividend with the reciprocal of the divisor, which is 8 over 1. We can cancel 4 and 8 because they are both divisible by 4. 8 divided by 4 is 2, and 4 divided by 4 is 1. Multiply, so 3 times 2 is equal to 6. 1 times 1 is 1, so we don't have to put 1 already. Our final answer is 6. So we can say Peter can make 6 packs of corn beets from the 3/4 kilograms of corn beets that he bought. That's it for our lesson for today. Our next lesson is on roots of numbers. Until next time, goodbye. 15 years, Anna's age will be the square root of 2025, or in symbol, we have this. What is her age now? You can solve for this problem if you are already familiar with square root. So the focus of our lesson for today is on this topic. So I hope that at the end of this discussion, you can answer this problem. Let us begin by defining what a square root is. It says here the square root of any number is a number whose square root is the given number. Well, that can be quite confusing if you are still unfamiliar with these terms. So let us have an example. We have here an expression 5 raised to 2, or it is read as 5 squared. Okay, so we call this number down as the base, and this number on top is called the exponent. It means that we would only have to multiply our base by itself based on uh, the exponent. So we will multiply 5 by itself twice because the exponent is 2. So the expanded form of 5 squared is 5 times 5. Okay, so that is read as the square of 5. Now, when we simplify this one, so we will obtain 25. Okay, now we will do the reverse. So this time we are going to get the square root of 25. This now is read as the square root of 25. So as you can see here, we have a symbol for square root, this symbol. It is different from the symbol for division, which is this. Okay, so for division, you have only a straight line and then a bar on top. But for square root, we have this tail. Okay, so that is written that way. Now, the square root of 25 is 5. Now, how did we get that? We have obtained that because we have identified, or we know that the number which we could multiply by itself to get 25 is 5. That's why it says in the definition that the square root of any number is a number whose square is the given number. Okay, so that is the definition of square root. We have here another example. So we also have negative 5 here as the base, and then it is squared. When we expand this, we will have negative 5 times negative 5. And based on our discussion on integers, when we are multiplying two negative numbers, the result is positive. All right, so we can then go back to our expression square root of 25, and square root of 25 can also be equal to negative 5. This means that the square of a number is the positive and positive and a negative number. Okay, so in this case, the square root of 25 is positive or negative 5. So it depends if it is asking for the negative root or positive root, so you choose between these two. But most of the time we consider only the positive root. Okay, but take note that we also consider the negative equivalent or negative additive inverse of the positive number or the positive root. Okay, so that's it. Let's continue. Now we have what we call perfect squares. 25 a while ago is an example of a perfect square. Okay, so we have here its definition. Perfect squares are numbers that have rational numbers as square roots. Again, rational numbers as square roots. In our next lesson, we will learn about the subsets of rational numbers.
Anyway, let's continue. The square roots of perfect squares are always rational numbers. Okay, so we will always come up with a rational number. So to have a quick preview of what rational numbers are, so this includes whole numbers, integers, as well as decimals and fractions. Okay, so we can obtain those rational numbers. Okay, so some common square roots of perfect squares whose roots are rational. So here are some examples. So our perfect square here is 4, but we have a lower perfect square which is 1. And of course, its positive root is 1 and its negative root is -1. Okay, followed by 4, because 4, the square root of 4 is 2 or -2. Followed by 9, 16, 25, 64, 81. The next perfect square here is 100. So its roots are 10 and -10. Let's try this. What is the square root of 49? So it is asking about the square root of 49. It means that we have to identify the number which we could multiply by itself to obtain 49. So what do you think is the result or the answer to this question? All right, the square root of 49 is 7 or -7. Okay, so either of the two or both. Next, we have what is the square of -2? This time we are asked about the square. We are missing the word root. It means that we have to multiply the number by itself twice. Okay, so that is the expression. So we have -2, the quantity squared. So -2 times -2 is +4. So this is the answer to this question. What is the next perfect square after 81? And we have answered that a while ago as well. The next number after that is 100. Since 81, the square root of 81 is 9. So the next number after 9 is 10. When we square 10, we will obtain 100. Next, what is the positive square root of 169? So it is only asking for the positive square root. And what do you think is the number? It is 13. Okay, when we multiply 13 by itself, the result is the number here. Okay, or the what do we call this? Perfect square. Next, so how about if we are given a fraction? Okay, we have a fraction inside the radical sign. So it says there the square root of the rational number of the form a over b, or the square root of ab, can be written and simplified by getting the roots of each term such that the square root of a over b as a whole is equal to square root of a over square root of b. So if it is squared as a whole, we can separate and square the numerator. I get the square root of the numerator over the square root of the denominator. So for this example, if we are going to do that, so we will get the square root of 4 and then the square root of 25. And when we simplify that, the square root of 4 is 2 and the square root of 25 is 5, which means that the square root of 4 over 25 is 2 over 5, or 2/5. So that is the positive root of this example. Okay, we could also include its negative root, which is -2 over 5. Number 2, find square root of 1 over 36. So again, we get the square root of the numerator and the square root of the denominator. Okay, the square root of 1 is 1. The square root of 36 is 6. So that is the positive root. We can also include the negative root or negative equivalent, which is negative 1/6. So the roots of 1 over 36 are 1/6 and negative 1 over 6. This time we will discuss about irrational numbers. So irrational numbers are any numbers that cannot be expressed as a quotient of two integers and are the roots of non-perfect squares. So a while ago, rational numbers can be expressed as the quotient of two integers, right? So this time irrational numbers cannot be expressed as such. So decimal numbers that are non-repeating and non-terminating are irrational numbers. You can check the previous lesson for more examples of rational and irrational numbers. Okay, there's also a note here saying that the square root of non-perfect squares are irrational numbers. Since they are not perfect, so obviously the answers are irrational numbers. Okay, so we have here an example of roots of non-perfect squares that are irrational numbers. So if you will use your calculator and get the square root of 7, you will obtain a non-repeating and non-terminating decimal, which is this, okay, which makes it an irrational number. Another one, square root of 65. If you are going to get the square root of that, you will obtain this number, and it is also non-repeating, non-terminating decimal. Number 3, third example, we have the square root of 315. So it is non-terminating, non-repeating as well. Okay, so we have here an activity. Classifying the roots of real numbers as rational or irrational. So let us check. The root of square root of 12 is 3.4641 and so on. Okay, so what do you think? Is it rational or irrational? It is not a perfect square, and as you can see here, it is a non-repeating, non-terminating decimal. So is it rational or irrational? Okay, it is irrational. And our analysis, the given or the root is non-repeating and non-terminating decimal. How about square root of 100? So square root of 100 is 10 and negative 10. Based on that, is square root of 100 a rational, or are the roots rational or irrational? So of course they are rational numbers because we know that these numbers are integers. Okay, and integers are rational numbers. And as you can see here in the analysis, 100 is a perfect square. Okay, and next one, we have here a decimal, 0.25, and here are its roots, positive 0.5 and negative 0.5. All right, so it is a rational number because it is a perfect square, although even though it is a decimal, but it is a perfect square and it is a terminating decimal. Next, the last one, we have 0.4. The square root of 0.4 is 0.63245. Okay, so what do you think is the result? All right, so the square root of 0.63245, the square root of 0.4 is equal to 0.63245, which makes it an irrational number because it is a non-terminating, non-repeating decimal. Okay. Next, we have what we call the principal nth root. Okay. So a while ago we have discussed about square root. Okay. So the principal nth root of a positive number is the positive nth root.
The principal nth root of a negative number is the negative nth root if n is odd. And next, note, the principal nth root of a negative number is not defined if n is given. Take note of all of this. And the notation for the principal nth root of a number b is the nth root of b. Okay, so b is our radical, and then we have here the root. Okay, so if it is square root, just simply like that. Okay, if it is like that, it is square root. But if we have a 3, a 4, or other numbers, so we will have third root or fourth root and so on. That's why we have here what we call nth root. So any number that can represent any number. Okay, so find the nth root of the following. So the first one is the nth root of number 1. So we have the cube root of 8. So that is equal to 2. Okay, so why is it equal to 2? Because when we multiply 2 by itself thrice, or 2 times 2 times 2, the result is 8. So this is an example of this one. Okay, since the radicand 8 is a positive number, the principal nth root of a positive number is the positive nth root. So the definition of this, from 2 cubed, which is equal to 8, this means that the cube root of 8 is 2. Next, number 2, we have the fifth root of negative 1024 is equal to negative 4. So take note, it says here the principal nth root of a negative number is the negative nth root if n is odd. Since n here is an odd number, we have 5, it is an odd number, so we will take the negative root of 1024, or its root is a negative number. That's why the result here is negative 4. Since when we multiply 4 by itself 5 times, 4 times 4 times 4 times 4 times 4, the result is 1024. And since the radicand is negative, so of course the result is a negative root. Okay, based on this definition. And next example, the fourth root of negative 81, it is not defined because based on this rule, the principal nth root of a negative number is not defined. Okay, take note. If the given, okay, is negative and it is asking for the nth root wherein n is even, so just say undefined, because if you key that in your calculators, that will be an error. Okay, so here are some common cube root, fourth root, fifth root of integers whose roots are rational. Okay, can you see here? So the cube root of 1 is 1, the third root of 8 is 2. So here are some of the most common perfect cube, perfect, what do we call this? For this is perfect cube. Okay, for this one, these are all numbers. Okay, for fourth root. Okay, so when we multiply 1 by itself 4 times, we will obtain 1, and then 2 times 2 times 2 times 2, we will have 16, and so on. We also have here for fifth root. Okay, so you can check it out before we proceed, or you can take a screenshot of this one, of this table. Okay, now we can proceed. So analyzing and classifying the principal nth roots of numbers. Let us try this activity. So we have 100, or square root of 100. So the nth root, it is asking for the radicand. Our radicand here is 100. And then the value of b, that is the value of b already. and then its root is 2. It is asking for the square root, so we are 2. Okay, as I have said earlier, if it is asking for square root, that means that we don't have to put 2 outside the radical sign. And the principal root of this is 10. Next, we have negative 81. Okay, first let us identify the radicand. Its radicand is negative 81, and it is also asking for the square root. So our root is 2, and it is even. And what did we say a while ago? If it is asking for the square root or the nth root, the given is negative and the root is even. So that is not defined. Okay, our third rule a while ago. Next, the fifth root of negative 32. So our radicand here is negative 32, and we are asking for the fifth root. So the root is 5, and it is odd. It is an odd number. Okay, by having an odd number, so it means, and a negative radicand, which means that our principal root is negative. We just have to identify the number which we could multiply by itself to get 32, and that is negative 2. Okay, so negative 2 times negative 2 times negative 2 times negative 2 times negative 2 is equal to negative 32. Next, that is read as the fourth root of 1296. Our radicand here is 1296. It is a positive number, and we are asking for the fourth root. So we just identify the positive root of this number, and it is 6. So 6 raised to 4 is equal to 1296. Next, the third root of negative 125. Our radicand is negative 125, and it is asking for the third root, so 3, and it is an odd number, so that is possible. But our principal root will be negative. Okay, so negative 5 as the answer to this. Next, we have the fourth root of negative 256. And when we get the radicand, we have negative 256. It is asking for the fourth root, and 4 is an even number. So this is same with the previous example. The second problem, this one, it is an even number, and the radicand is negative, so it is not defined. Okay, not defined or undefined. Last, we have negative square root of negative 25. All right, so we have negative 25 as the radicand, and we have 2 as the root. 2 is an even number, and we have a negative radicand, so it is also not defined because that is not possible. Okay, for the next lesson, we are going to determine between which two integers the square root of a number lies. Okay, determine between which two integers the square root of a number lies. Example 1. Between which two integers the square root of 20 lies. So we just have to think of the perfect square near 20. And what are those numbers? Okay, let us recall first. Let's start with 1, followed by 4, and then the next one is 9, 16, 25, 36, 49, and what's next? 64, 81, and 100. So that is from 1 to 100. Those are the perfect squares. So we are it is asking between which two integers the square root of 20 lies. So we have the numbers 16 and 25. Okay, so square root of 16, and then we have square root of 25. That is where we can find square root of 20. So we have here square root of 20, and then we put our notations this way. Okay, so square root of 20 is greater than square root of 16, but it is less than square root of 25. And we know what is the value of square root of 16, that is equal to 4. And then square root of 20 is not a perfect square, so we copy it as is. And then square root of 25 is 5. Now the answer to this example is 4 and 5. Square root of 20 lies between 4 and 5. All right, there. So this is our rule on how we have obtained our answer. To approximate the value of roots in a given number, we must determine between which two integers the square root of a number lies. All right. So that is the same solution that I've shown you. So again, the answer is 4 and 5. Square root of 20 lies between 4 and 5. Next example. Example 2, between which two integers the square root of 75 lies. Okay, so by now you should already be familiar with those perfect squares from 1 to 100. So the nearest perfect square to 75 is 64 and 81. Okay, so we should consider the square root of 64 and square root of 81. So the square root of 64 is 8 and the square root of 81 is 9. So the answer here is 8 and 9. We can find 75 between these two numbers. Okay, because square root of 75 is greater than square root of 64 but less than square root of 81. Again, for the solution, so here 75 lies between 64 and 81. Okay, so if we are going to write them using the these symbols for inequality, so we have 64 is less than 75 and 75 is less than 81. And until we find the final answer, which is 8 and 9. So again, square root of 75 lies between 8 and 9. Example 3, between which two integers does 247 lies? So for this, you can do trial and error. Okay, since we have only obtained 100 a while ago, so we stop from to 100. So the next perfect square after 100 is 121. So that is the product when we multiply 11 times 11, and the 12 times 12 is 144. Okay, let us list that down, and then we will when we multiply 13 times 13, the result is 169. Okay, and then followed by what is this? So this is 11 times 11, 12 times 12, 13 times 13. How about 14 times 14? What is the result when we multiply 14 by 14? So we have 196. Okay, we're almost there. Next, let's try 15 times 15. The result is 225. And then the next after that, we have 16 times 16. The result is 256. Okay, so it is between these two perfect squares. Okay, it is between 225 or between the square root of 225 and the square root of 256. So this is 16 a while ago, right? If you're going to get the square root of this perfect square, it is 16 and this is 15, which means that square root of 247 is between 15 and 16. Again, here is our solution, and yes, it is between 15 and 16. For the next lesson, we are going to estimate the roots of a number. So this is quite familiar with our last lesson, okay, which is on estimating roots of what is this? Identifying between which two integers an irrational number lies. Okay, so again, our lesson or our next lesson is on estimating the roots of a number. Once again, this is teacher Mary Jane. Let's continue. Okay, conversion of radical numbers to fraction by approximation method. So this is the easiest method, right? So we will just approximate, but we will do trial and error. Okay, number one, find two consecutive perfect square integers between which the given number lies. So this is what we've done earlier. Next, find the distance from each integer. Okay, so we have to find the distance between these two integers. The distance of the radicand to the first integer is the numerator, while the distance of the two perfect squares, again, while the distance of the two perfect squares is the denominator of the fraction. Take note of that. The square root of the first perfect square integer will be the whole number and affix the fraction form to form a mixed number. Okay, that is quite complicated, but we can follow that as we answer some examples. Let's have example number one. So we follow the steps earlier to convert the square root of 40 in fraction form. Okay, so first we have for step 2, find the two consecutive perfect square integers between which the given number lies. Okay, this is just an extra part, so let us erase that. So square root of 40 lies between square root of 36 and square root of 49. Next, find the distance from each integer. The distance of the radicand to the first integer is the numerator, while the distance of the two perfect squares is the denominator of the fraction. Okay, so when we apply this, so we are going to find first the distance between 36 and 40. So 40 minus 36 is 4, and it says there 4 will be our numerator. So here is our fraction. And the next, while the distance of the two perfect squares, our two perfect squares here are 36 and 49. Okay, so when we subtract 49 minus 36, we will obtain 13. And that will be the denominator. So we have 4 over 13. The square root of the first perfect square integer will be the whole number and affix the fraction form to form a mixed number. So again, we go back to square root of 36. The square root of 36 is 6. That will be our whole number. And for our final answer, the approximated value of square root of 40 is 6 and 4 over 13. I hope you were able to follow those steps. Let's have another example. Okay, let us try to answer this activity. So we have the square root of 5. So let us approximate its value in fraction form by following the steps a while ago. Okay, so we have here the perfect square between which we could find the square root of 5. So it is between the square root of 4 and square root of 9. So 4 here is our A, and 9 is our B, and 5 here is our N. Okay, do not be confused. So that is N, A, and B. So when we subtract N minus A, so 5 minus 4 is equal to 1. After that, we subtract the value of B minus A, so the difference between these two numbers. So 9 minus 4, so that is equal to 5. And then we get the square root of the first integer. Our first integer is 4. The square root of 4 is 2, so that will be our whole number. We can now write them as a fraction. So our whole number is 2, and then our fraction is 1 over 5. Next, the square root of 29. So it is between the perfect squares 25 and 36. Then we subtract the value of b, or 29 minus the first integer. 25 minus 29 minus 25 is equal to 4. So that will be the numerator of our fraction. And then we subtract 36 minus 25. And we will obtain 11. 36 minus 25 is equal to 11. Now the square root of 5 is 5. The square root of 25 is 5. So this is our whole number. So writing them as a fraction, we have 5 and 4 over 11. Number 78. Number 3, so we have square root of 78. It is between 64, or square root of 64, and square root of 81. And then we subtract 78 minus 64. The result is 14. Next, we subtract the two perfect squares. 81 minus 64. The result is 17. So that is our denominator. Now we get the square root of 64 again, and the result is 8. We write them as a fraction, so square root of 78 is approximately 8 and 14 over 17. Next, how about the square root of 162? So it is between 144 and 169. So subtracting 162 minus 144, the result is 18. And then 169 minus 144 is 25. And the square root of 144 is 12. So we can now write it as a fraction. So we have 12 and 18 over 25. Now that we already know how to approximate the value of an irrational number, we can now plot them in a number line. So we have here an example. So we have letter A, square root of 5, B, square root of 29, C, square root of 78, D, square root of 162. So let us do a quick solution, or let us show a quick solution for this one. So square root of 5 is between the square root of 4 and square root of 9. So let me write it that way. And then to approximate its value, so we find first the whole number. So square root of 4 here is 2. And then the difference between 5 and 4 is 1. That will be our numerator. And then the difference between 9 and 4 is 5. So that is 2 and 1 over 5. Next, for letter B, we have square root of 29. So when we square root of 29 is between square root of 25 and square root of 36. Okay, so let me write it first. That means that our whole number is 5. And then subtract these two. We have 4 as the numerator. 36 minus 25 is 11. So we have 5 and 4 over 11. Square root of 78 is between square root of 64 and square root of 81. So we have 8 as our whole number because we have your square root of 64. And then subtract this two. 78 minus 64. We have how many? 12. Am I right? Yes, 12 over subtract 81 minus 64. So this will be 11. 11 minus 4 is 7. So we have 17. 8 and 12 over 17. Next, square root of 162 is between the perfect squares 144 and 169. Square root of 144 is 12. And then 162 minus 144. Let me subtract that. So this will be 12. This will be 5. So 12 minus 4 is 8. So 18. And what's this? 169 minus 144. The result is 25. Wait. So 12 and 18 over 25. Let us check if it's correct. Yeah. So yeah, letter 8, square root of 5 is approximately 2 and 1/5. Square root of 29 is approximately 5 and 4 over 11. Square root of 78 is approximately 8 and 14 over 17. 14. Yeah, 12 minus 4 is 12 minus 4. Alright, so this should be 14. Wait. So this should be 14 because 78 minus 64 is 14. I'm sorry for that. So again, this is 14. This should be 14. And then for letter D, square root of 162 is equal to 12 and 18 over 25. Correct. We can now plot them in the number line. So letter A, 2 and 1/5 is approximately here. So we write the original given, which is the square root of 5. Okay, so it's up there. And then we have the value of square root of 29. Again, 5 and 4 over 11. So it is approximately in this part. Square root of 78 is equal to 8 and 14 over 17. So it is approximately in here. And then square root of 162 is approximately 12 and 18 over 25. So it is approximately in this part. All right, so that is how you plot irrational numbers. All right, so to check your understanding of our lesson, so let us try to answer this activity. So in the first column, we are going to identify the radicand. Second column, the root, and then the principal root. Okay, first we have the radicand 100, 6,561, 243, negative 729, 3,125, negative 4,096, 7,776, negative 1,000, negative 121, 16,807. Now let us look at the roots. So square root, we have the fourth root, fifth root, cube root, fifth root, fourth root, fifth root, cube root, square root, and fifth root. So let us identify first if there are not defined or the principal root is undefined. If the given radicand is negative and the root is even. So this is negative, but the root is odd, so that is okay. Here we have a negative radicand and it is even, so this is not defined or undefined. Next we have here a negative radicand, but it is odd, so that is okay. The root is odd, but for the last one or this one we have negative 121. It is asking for the square root. Square root is even, so that is also not defined. Okay, I think we can now solve for the roots of the given. So when square root of 100 is 10. Fourth root of 6,561 is, what number can we multiply to get the value of 6,561? So this is 9. Next, the fifth root of 243. So the result is 3. And then the third root, or the cube root of 729. Since it is a negative number, so the answer is negative, and that is 9. Next, 3125, its fifth root. So the answer here is 5. Next, 7,000, the fifth root of 7,776, and that is positive 6. Next, it is a negative number, so the result there is 10. And for number 20, 16,807, fifth root of 16,807, and the result is 7. Next, activity. For this activity, we approximate the square roots to fraction form. The first one is done. Okay, so square root of 15 is between the perfect squares 9 and 16. Square root of 39 is between 36 and what's next after 36? 49. Next, 50 is between 49 and 64. 83 is between 81 and 100. 152 is between 149 and what's next after 149? I mean, it is 144, not 149. Let me erase that. Okay, so what it is between 144 and 169. Next, we have 225, and it is between 225 and 256. Square root of 319 is between 289 and 324. 399 is between 361 and 400. Square root of 415 is equal to is between 400 and 441. Square root of 815 is between 784 and 841. Now let us subtract n minus a first. So 15 minus 9 is 6. 39 minus 36 is 3. 50 minus 49 is 1. 83 minus 81 is 2. 152 minus 144 is 8. 253 minus 225 is equal to
28. 319 minus 289 is equal to 30. 399 minus 361 is equal to 38. 415 minus 400 is equal to 15. And then 815 minus 784 is equal to 31. Those are our numerators. Let us subtract b minus a. Alright, next column. So subtract the perfect squares. So 16 minus 9 is 7. 49 minus 36 is 13. 64 minus 49 is 15. 100 minus 81 is 19. 169 minus 144 is 25. 256 minus 225 is 31. 324 minus 289 is 35. 400 minus 361 is 39. 441 minus 400 is 41. And 841 minus 784 is 57. And then square root of the, what's this? The square root of the first integer. So first, the square root of 9 is 3. Square root of 36 is 6. Square root of 49, 7. Square root of 81, 9. Square root of 144, 12. Square root of 225, 15. Square root of 289, 17. Square root of 361 is 19. Square root of 420. Square root of 784 is 28. Alright. So we write them as fractions now. So number 26, we have 3 and 6 over 7. Number 27, we have 6 and 3 over 13. Number 28, we have 7 and 1 over 15. Number 29, we have 9 and 2 over 19. Number 30, we have 12 and 8 over 25. 31, we have 15 and 28 over 31. Number 32, 17 and 30 over 35. Wait, let me check that. Yeah, so it's correct. So we can still simplify this. 17 and 6 over 7. Next, we have 19 and 38 over 39. Next, 20 and 15 over 41. And the last one is 28 and what is this? 31 over 57.
Hello, dear learners. Today we are going to learn about the set of real numbers. This is teacher Mary J. First is the set of natural numbers represented by letter N or counting numbers. So these are the numbers that we use to count. When we are counting, we always start with 1. That's why the lowest counting number or natural number is 1, followed by 2, 3, 4, 5, and so on. Okay, so in this diagram, this is where we find the set of natural numbers. Then, the set of full numbers are the union of the set of 0 and natural numbers. So just include 0 to the set of natural numbers. So instead of starting with 1, we start with 0. Once we've included 0, so that is considered the set of whole numbers. Okay, so as you can see in this diagram, whole numbers cover natural numbers. Okay, it covers natural numbers. It means that natural numbers is a subset of whole numbers, the set of whole numbers. Next, the set of integers are the union of set of whole numbers and negative whole numbers and negative natural numbers. Okay, so we have and of course 0. We also include 0 here. Oh yeah, 0 is already included in the set of whole numbers. Okay, so here is our notation for integers. We use letter Z. And here are the sets. So we have -5, -4, and we have ellipses here and ellipses here as well. It means that it is an infinite set. Okay, so it has 3 subsets. The set of positive integers, and then we have the set of negative integers, and then the set including 0. Okay, so here are the notations for those 3 subsets. Okay, so in this diagram, integers is this circle, is represented by this circle. So again, it covers the set of whole numbers and natural numbers. The next one is the set of rational numbers. These are the union of the set of integers, fractions, and decimals. But take note, not all decimals are rational numbers. This should include the terminating and repeating decimals. They are numbers that can be expressed as a ratio or quotient of 2 integers, a over b, wherein b is not equal to 0. Okay, so here are the examples of rational numbers. By the way, we use letter Q to represent rational numbers. All right, so we have -5, so that is a negative integer, -2/3, that is a negative fraction, and then 0, 3.75 a decimal, and then 5 a positive integer. Okay, so it is represented by this whole circle, which covers integers, whole numbers, and natural numbers. Next, let us define irrational numbers. So irrational numbers, on the other hand, are numbers that are non-terminating, non-repeating decimals, or radicals whose roots are not exact. So here are some of the examples of irrational numbers. So if rational numbers are represented by q, so q prime means that the number is an irrational number. Okay, so here are the examples: negative square root of 5, this decimal which is non-terminating and non-repeating at the same time, and then the square root of 2, the value of pi. Okay, so it is represented by this circle on the right. Now let's have these illustrative examples. So given 15, negative 12, 0, 9.35, 5 over 7, 8.25, and so on. The square root of 12, 8.25 with a bar on top, and then square root of 9. So which are irrational numbers? So let us identify the irrational numbers first. So square root of 12 is an irrational number, as well as this number, because it is non-repeating, non-terminating decimal. Square root of 12 is also an irrational number because it is not a perfect square. Okay, and it cannot be expressed as the, what do you call this, as the quotient of two integers. Letter B, which are rational numbers? Of course, when we remove these two, the remaining are 15, negative 12, 0, 9.35, 5, 7, 8.25, and square root of 9 are rational numbers. Okay, 15 is a positive integer, negative 12 is a negative integer, 0 is an integer, 9.35 is a decimal, 5 over 7 is the fraction, and then 8.25 with a bar is a repeating decimal, and square root of 9 is equivalent to 3, so that is an integer, okay, or a perfect square. So these are all rational numbers, which are integers. So integers are 15, negative 12, 0, and square root of 9, again because the value of square root of 9 is 3. Which are whole numbers? Whole numbers include 15 and 0. And last, all right, next we determine which of the following is true or false using this notation. So N for natural numbers, W for whole numbers, Z for integers, Q for rational numbers, I for irrational numbers, R for real numbers. Number 1, 25 is a natural number. Yes, that is true, because natural numbers starts from 1, 2, 3, and so on. Letter B, 1.125 is a rational number. So that is true because it is a terminating decimal. C, negative 3/5 is an integer. Of course not, because it is a fraction. So it is false. D, square root of 39 is an irrational number. This is true because 39 is not a perfect square. E, 0 is a natural number. Well, we have said earlier that 0 starts, or natural number starts from 1. So this is false. And F, square root of 100 is an irrational number. Since square root of 100 is a perfect square, so this is also false. Okay, next example, plot the set of real numbers in the number line, then rearrange it in increasing order. So we have positive 5, negative 8, 0, 11 thirds, negative 7 over 9, square root of 6, and the negative value of pi. Okay, so we have here the approximate values of the other numbers. 11 thirds is approximately 3.67. Negative 7 over 9 is approximately 0.78 or negative 0.78. Square root of 6 is approximately 2.45. The negative value of pi is approximately negative 3.14. Okay, so we can now plot these numbers given this equivalence. So 5 is very easy, so just plot it here. Negative 8 is here. 11 thirds is approximately 3.67, so it is between 3 and 4, so almost here. We have passed 0, so 0 is here, and then 3.67 is here. Negative 7 over 9 is approximately 0.78, so it is negative, so it is here between 0 and negative 1. And then square root of 6 is approximately 2.45, so it is here. Next, negative pi, so negative 3.14 should be here. Okay, let us move that. It should be here. Okay, let me remove that and put it here. Okay, so it should be here. Let us put an X on that. That is wrong. And we will extend this. Okay, so that is the answer for negative 3.14. So in increasing order, we start with the lowest, which is negative 8, followed by negative pi, followed by negative 7 over 9, followed by 0, followed by square root of 6, and then 11 third, and the largest number is positive 5. Well, thank you so much for listening to that discussion. Our next lesson will be on scientific notation. Once again, thank you so much for listening. This is teacher Mary Jane. Until next time, goodbye. Hello students, we are now done with the last lesson for the first quarter, which is on scientific notation. Once again, this is teacher Mary Jane, and I hope that you listen to our discussion for this session. Which of the following is written in scientific notation? All right, so based on the definition earlier, which of the following? So number one, so as you can see, it is 12.78 here is greater than 10. So this is not written in scientific notation. Number two, it is less than 1. So this is also not written in scientific notation. Okay, so for number one, 12.78 times 10 raised to 8 is not in scientific notation because the decimal number is greater than 10. Number two, 0.134 times 10 raised to 5 is not in scientific notation because the decimal number is less than 1. Number three, this is also not in scientific notation because the exponent here is not an integer, it is a decimal. Number four, 1. So we have 1 as a number, and then negative 3 here is an integer, so that meets the requirement for scientific notation, so it is in scientific notation. Next, 2.1 is in between 1 and 10, including 1, so that is, or yeah, it is between 1 and 10, so this is okay. And then 6 here is an integer, so this number is in scientific notation. Okay, so we have here the steps on how to change decimal notation or changing the decimal notation of a number to scientific notation. So number one, place the decimal point after the first non-zero digit. Count the number of places the decimal points is moved and use that number as a number or integer exponent. If the original number is greater than 10, the exponent is positive. If the original number is between 0 and 1, the exponent is negative. Okay, so let's go. Another here, we have a note. If the movement of the decimal place is to the left, the exponent is positive, and if the movement of the decimal place is to the right, then the exponent is negative. We have here an example. So we have 240 million. Okay, this is obviously greater than 10, so our exponent will be positive. So let us move first our decimal point. So the decimal point of this is here. Okay, so if we are going to change that, we will show that later on. So let us just look at it as examples. Okay, number two, another example. So we have 9,877.234 or 9,877 and 234 thousandths. Number three, 42 is also a number greater than 42, and a number greater than 10. So it is it will have a positive integer as an exponent. Okay, now let us try to write them as scientific notation. So the decimal point of this number is here, and then we will move to the left, okay, until the last until this point, okay, so that we will have 2.4 as our number, and then multiply it by the number of places at 10 raised to the number of places we've moved. So we have 1, 2, 3, 4, 5, 6, 7, 8. So 10 raised to 8. Again, it is we move to the left, so it is positive. Next, number 2. So we have to move this until this point, until the point between 9 and 8. Okay, so we have 9.877234. Make sure that we include all of the numbers, and then times 10 raised to 3. Number 10 raised to 3 because we moved 3 places to the left. Number 3, 42. So the decimal point is after 2. We can only move 1 place to the left. So when we rewrite that in scientific notation, we have 4.2 times 10. 10 raised to 1, or simply 10. Okay, next example. So how about if we are changing these numbers lower than 0, okay, which no, numbers between 0 and 1. So when we change them, we move to the right. Okay, so it will have a negative exponent. Okay, so for number 1 we have 0.00042. Okay, so we will move our decimal point to the right. How many times? 1, 2, 3, and 4. So that is our exponent, -4, and then we have 4.2 as our number. Number 2, we have 0.00125, so we stop in between 1 and 2. So we have 1.25 times 10 raised to -5 because we move 5 places to the right. And number 3, we will only move 1 place to the right. So we have 2.5 times 10 raised to 1. Okay, last we are going to learn how to write scientific notation in decimal notation. So it's standard form. So if we have a positive exponent, so we will do the reverse. Instead of moving to the left, we will move to the right this time. Okay, so we have 6.25, that is our number. So we will move to the right based on the exponent 5. So 5 places to the right. So there. Now, if you can see, we have black spaces here. So we are going to annex zeros. Okay, so 6.25 times 10 raised to 5 is equal to 625,000. Number 2, 9.68 times 10 raised to 3. So we will move the decimal point 3 places to the right. So we will only move 1, 2, and 3. So we have to annex 1 0. And the equivalent of this is 9,680. Okay, how about if we have a negative exponent? So we have 2.17 times 10 raised to -3. So we have 2.17. This time we will move to the left 3 times. So we have 1, 2, and 3. The decimal point will be here. All right, and we have to annex zeros. So the result is 0.00217. Number 2, 7.25 times 10 raised to -5. So 7.25 is the number. We will move 5 places to the left. So we have 1, 2, 3, 4, 5. The decimal point is here. And we have to put zeros in the parts that have no digits. Okay, so the simplified form, we have 0.0000725 as the equivalent of 7.25 times 10 raised to -5. All right, so that ends our lesson on scientific notation. So it also ends our lesson for the first quarter. So I hope that you learned from this video. Thank you so much.